Kirti, you want to try? Come. You can pick up the microphone and yeah. Microphone. They had a microphone, no? Speak on the microphone. Yeah. He'll give you that.
Hello.
So yeah, first we started with teaching. What's the teaching mean? Then learning. Then we discussed about what we'll discuss today. Yesterday, like what does power electronics mean, and what does electronics mean in the second session. Then we discussed about the diode. Like to know about the electronics, we discussed about the diode. Then you asked about to draw the how diode looks and all, and how the diffusion works and how drift velocity and all be done. Then at last the question is like, can we use this diode like as an amplifier?
So
How
something
can
between
we
them.
use
So after we started drawing the depletion layer, what did we do? So was there something that we did after doing the depletion layer?
Yes, sir.
Nothing. We just drew the depletion layer and said this is the diode.
No, sir.
What did we do?
We discussed about electric field and the exponential curve of that.
Why is there an electric field there?
Because the charges accumulate, like the holes
The
and
charges
electrons
are there.
recombine
They're
together where the
So-
electric field will produce.
Okay, so we discussed about the electric field near the PN junction,
Yes, sir.
right? That's what we discussed for a long time. So, okay, and did we understand anything out of that? Electric field near the PN junction?
Yes.
What was your understanding about that? Is there a field?
Initially, when the electric field will increase from the negative side to the positive side, and where there will be a maximum electric field at the junction, like
at the middle. So
at the
the
middle,
electric field, the depletion layer.
Yeah, at the depletion.
Electric field is very high around the depletion layer. It is at the peak at the metallurgical junction, the two ends. So that's what we saw. There's a very high electric field, and electric field is related to voltage, right? Our voltage is related to electric field, right? How is they related?
D by dx is equals to using Gauss law, we derived that D by dx is equals to minus rho b by epsilon naught, where rho is the density of that.
No, but electric field and voltage, right? What is the voltage across the depletion layer? How do you calculate the voltage across the depletion layer? Yeah. Okay, thank you so much for coming and saying whatever. Can I ask someone else to? Yeah. Please, someone else can come and give your perspective what happened yesterday, like Kirti did. Why don't you come? Last man there. Oh, you can also come. Yeah. Yes, come. Yeah.
Hello. We started with the title of the workshop. After that, we have discussed about the two questions like what is electrons and what is diode actually. And the question is like electronics means, is it a study about the study on the electrons and all actually? So Sir has given Sir has clarifying that question, and later on we'll move to the diode, and after that diode, so Sir was explained about the equivalent actual model of the diode, actual representation of the diode, and general representation of the diode, the difference, what is the difference between the actual representation and general representation, whether it is acceptable, general representation is acceptable as like actual representation, and what is the, so whether if it is acceptable, what makes it is acceptable thing, like what is the important things to be accepted. After that, we slowly move on to the depletion layer. So in the depletion layer, Sir has discussed about the charges, electric field intensity, where it is higher electric field intensity and where the concentration is high. Like all this discussion because of the question like how we will increase the voltage blocking capability of the that particular power diode, like how we will move the normal electronic diode to the power diode. So what perspective we have to increase the voltage level, voltage blocking capability of the diode, like by discussing on the depletion layer, the electrostatic effect on the effect in the depletion layer. So later on, the characteristics of the diode and the relation, what is the voltage relation and current relation, how the current is exponentially increasing by changing the little amount of voltages. So that feature we have to, whether it is, that feature we have to use as a amplification, use it for the amplification. Later on, we will move to the BJT, whether this feature, is it possible to implement with the BJT for as a amplifier. That is my understanding according to the studies.
Very good summary. What's your name? Raghavendra. You are a research scholar.
Yes.
Very good. Raghavendra has given a very good summary. So, yeah. So, does anybody want to add anything? Yeah, just you can check with them if there's anybody has any question or something. He says only you could do that. That's what he was saying. That you are in the teams and therefore only you can do that. Ah. Yes, Tariqul Islam is there. Ah. So, are the online audience able to hear me? Can someone confirm that, please? Professor Tariqul Islam is also there. Hello, online audience. Anybody is able to hear me? Okay, I think we'll move on. Maybe, please feel free to raise a hand and Vaijayanti madam will, pass on the question here. Huh? Sure. Online audience, yeah. I couldn't speak to you yesterday, but raise your hand whenever you have a point. Okay, yeah. All right. So I think you can have this. Does anybody want to add any point on what happened yesterday? Yes.
More than mathematical expression of how charges are distributed in the depletion layer, we were able to visualize it. Like if it is just a charge, one positive and negative, and how the flux line flows from positive to negative, we put the same visualization in the depletion layers and where the intensity is high. So instead of just drawing the slope and putting the equation, we were able to draw the electric field lines and then understand the concept why it is increasing and decreasing. So that was a eye-opener study.
Very good. Thank you, madam. Anybody else wants to say anything? Everybody is fine? Okay. So you can keep that somewhere there at the middle. Yeah. Yes. Yeah. So just to conclude yesterday, okay, we were talking of electronics, but a lot of time was actually spent on electromagnetism, particularly electrostatics. We're talking of electronics. Why electronics, right? Why do you call that, etc.? So we went into the old diode, that is two-terminal vacuum electronic diode, right? There, that's a historical name. There, it is entirely based on electromagnetic field, and after the semiconductors have come, we somehow are not focusing so much on the electromagnetism inside. We are focusing more on the terminal characteristics. So that is probably one. So a lot of time yesterday went on electromagnetism. So electrostatics we were discussing. We were trying to visualize the field firstly. From the charge density, we were trying to visualize the field. Then we were trying to quantify the field. That's when we needed Gauss' law. And then we went into all kinds of things, right? One by one, we did many things related to that. So as I start, based on yesterday's session, I have a few requests. I think I have to put my, here, how does it work? Pen, no? Oh, this needs a pen. Okay. Yeah, here I can choose the pen, I think. No, that's all. So I just have some requests. What is the request? Teachers. Huh? Yeah. Okay, thank you. So I have a request for teachers. So what is the request? Those who are teaching electronic devices, right? Those who are teaching electronic devices. So please cover the electric fields. Please cover the electric fields. Historically, the books used to do that. From charge density, they used to go into the electric field and come to that. Now, I think everybody is shortening. So, many a times, some picture is given and some voltage is given, and some explanation qualitatively is given to the students. So, the voltage is high here and low here, etc. So, my request to the electronic devices teachers, I don't know who is teaching what subject here and whether they are there. My request to electronic devices teachers is to see how they can cover electric field, because it will be very meaningful, and you will go from the charge density, etc. You go to electric field, and then you can go into the voltage. You can be able to do a very good job of that. Again, my request to teachers who are teaching electromagnetism. Those who are teaching electromagnetism, take electronic devices as examples. So specifically, I haven't talked much about that. I've talked only about diode. In an electrostatics class, you can say that this is how there is charge accumulation there, and this is how the electric field could be calculated in, around the junction in a diode. So this could be something done in the electro class, and I request the students to apply your knowledge mutually. What you have learned here, you apply there, and vice versa. Again, there's a specific request for students. I have a request for students. Now, what is that? Please take care of electromagnetic fields. Okay. Just don't say that, oh, third semester somehow I passed, I've got some grade, right? I've got some B plus A, something, okay, and leave that. And plus vector calculus. So I'll also tell you why. I'll give you examples, something that we have already covered. If you want to understand electronic devices, right, you certainly have to understand fields. We were discussing that yesterday for a long time. That was also the reason. Next, we will go to magnetics. Hopefully, we will do it towards the end of the day today, the last session. The magnetics, you have to understand a lot of magnetic fields here. Okay. It could be static fields. It could be time varying field. And there could be more dynamics involved also. I'm saying most. Then if you go to machines, which we will probably do the whole of tomorrow, machines and their control, here also, here you have to go further. Okay. Magnetic field, because of that, what happens to eddy current and all that. So unless you have a hold over fields and vector calculus, an in-depth understanding of all this is not going to be possible. If you have to understand an electronic device, you have to understand the active area. The active area in the case of a PN junction diode is the PN junction. The active area in a MOSFET would be the channel, which we'll discuss from now. All these are places where the fields are very high. They are very intense. And the knowledge of those fields are essential for you to understand what's really happening, functioning, why is it failing, right? To get the basic physics from that. And remember, as I mentioned in a tea time conversation, whenever you use a device, the internal information will not be available to you. The internal information will not be, only the data sheet will be available by the manufacturer. You will have to go ahead and generate more data if you require. You should have the experimental capability to do that. So you have to work with the terminal one. And the internal details is normally the textbook's details. That is, only if you know the fundamentals well, you will be able to say, perhaps this is what is happening. You understand my point? It's going to be a black box. They are not supposed to tell you what is all internally there. They'll tell you the terminal characteristics. But if you have your basic understanding, you will be able to make a very good use of that. So that's my request to you. That is about magnetics, machines, practically every kind of device. Many kinds of devices use electromagnetic fields. So don't just deal with it as one subject, how that is gone on this vector calculus. And you can see vectors become scalar, right? Scalars are related to vectors. So don't take vectors as some, alien planet thing or something. And similarly, magnetic fields are circuits, or circuits are fields rather. Circuit is a very special case of a field. That's something that we will do in our magnetic session. So right now I'll pose the question. You have heard the term called field, right? You have heard the term called circuit, right? Are they same? Are they different? How are they related? The question is clear. Okay, be ready with your answer later in the afternoon when we do the magnetics. Okay, yesterday itself we did quite a few things to start off with that. What is the question? What do you mean by a field? What do you mean by a circuit? How are they related? Okay, yeah, take that as a question. Those are very important for you. And these are all not only from the textbook point of view. I'm going to tell you whole of the modern power electronics, the modern day power electronics. What is the trend? You are having devices that are switching very fast. You are having devices, so the d by dt is very high, dv by dt, da by dt, whatever is very high. So you have very fast switching. And when you have fast switching, you will have high frequencies. Switching is in terms of fastness, in terms of time, and in the frequency domain, these are high frequencies. So as a result, you have to develop understanding in terms of magnetic fields. You have to certain understanding of magnetic fields is required. Complete electromagnetic field for it to do this now. One more important thing I will add here, which we are not covering, is how do you deal with insulators? That is electric field. We were at the starting point. So with this discussion, you can go forward and understand what is happening in insulator. Current flowing through the insulator is a problem, right? That's what happens through dielectrics. This is what happens in EMI and other things like that. So these are what are the basic subjects. And for high switching frequency power electronics, right? It's not really a circuit, it is all field. Actually speaking, it is all field that's really happening there. We are somehow dealing with them. So that will help you deal with that. I'm not getting into the what are the challenges, how exactly. But the challenges concerned with them, you will be equipped to deal with that if you have a better understanding of electromagnetism. So that's my broad request to that. I'll be happy to talk to the specific teachers if they need anything on that. Somehow, whenever we get time to do that. Those who are teaching either electromagnetism or devices, I can certainly talk to them sometime. Okay. So now let me go to the next slide. I should say plus, is it? So today, we have been going a little this thing. So let's put some what we would do today. Let's try do the BJT and MOSFET in a short while, right? This is one. Then another way I'll put this, let us understand analog, digital, and power electronics. Okay, let's try and understand. All these use transistors. All these use transistors. But there's something called analog, something called digital, and something. We'll do this now. And in between the two, you have one issue. Okay, that is where I see a lot of problem. Analyze circuits, okay, with electronic devices. So this is where I think sometimes we run into issues. Okay, this should come somewhere between the two or interspersed there. So this is something I would like to complete as the basic understanding of electronics and gearing towards power electronics. And in this, one important thing will be the IV characteristic. And that IV characteristic is what will be emphasized in coming to switching, okay, transients. Switching transients or transitions you can call, right? It is also called switching transitions. That is a better terminology in power converters. This will be very helpful in finding out that, and also how do you analyze a circuit. How is the switching transient? A transistor turns on, turns off. How does it turn on? How does it turn off? What happens to the current that is flowing through that? How does it, who is sharing? How is it getting shared? Right? What is the waveform? Ideally, they turn on and turn off. It's an instantaneous process, but that's not the case. So here is a very, very fundamental point in understanding, without which you will have any difficulty in understanding or realizing a practical inverter. This is, I would call that as a very hardcore power electronics. This is a big challenge even to many trained power electronic engineers I found. So this is something that I would like to emphasize. From that particular point, I would like to go into power converters, where we'll at least do simple things like buck, boost, synchronous buck, then a voltage source inverter. So we'll do this. Again, all this will not jump. This is how the circuit is, and that is how it works. We'll try to go to a more fundamental point and see if I want to do this conversion, what should I do? How should I connect my switches? Is the approach clear? That's what we will try and do. So then this is over. This is the reason I was saying these are very important for power electronic fundamentals, and those require that. You can't understand the switching transitions without that being clear. That is why I repeatedly told a number of you in the morning, if you and your friends are interested in power electronics, please attend today's session. That was the reason I said that. And towards the end, I'll go to magnetics. The magnetics, I'll talk about field, what do you mean by magnetic circuit, and right, what do you mean by magnetic field, magnetic circuit, and then about magnetic materials, correct, which will lay our foundation to move towards inductors and transformers. Okay. This will be our endeavor today, so that tomorrow we have all the fundamentals in place about electronics, magnetic fields, magnetic circuits, electric fields, circuits, right? Field circuits, all the knowledges are there. We'll try to go into machine, and we know how to shape a magnetic field and all that. Again, I'm telling you, magnetic fields are very important. Electric fields are very important, as we recognized in diode yesterday. We will, whenever you see, you will continue to see that. Okay, that is true about machines also. Okay, biggest thing is we are very, very blind to the magnetic fields inside, and the magnetic fields can be understood more easily as magnetic circuits. We don't even understand the magnetic circuits inside a machine. The moment an induction motor is given to you, most of you will draw an equivalent circuit. Okay, so that basically means a lot of details are lost. It is only equivalent circuit is only a terminal representation. It says that between the two terminals, the motor is equivalent to the circuit, and the motor is not that circuit. Many of this knowledge was there in the derivation, but you would not have done rigorously, and what you would have done, you would have forgotten. So all that is gone. So machines will have to be understood in terms of the magnetic fields inside them, and how those magnetic fields have to be reduced into magnetic circuits. And from those magnetic circuits, we have to look at energy, how energy, stored energy will vary, what is torque, what is force, right? We have to look at such things and develop an understanding. God willing, we'll do that at a similar time tomorrow morning. And then we'll also, by then we have also picked up something on the power converter. So we'll be able to go to drive control of those motors, and we'll be able to flip over the motor control easily to do converter control. They are closely related. So that's what we'll do tomorrow. Is it clear? Okay. So let's do this now. I think some of you have studied how is BJT done and all that. A lot of historical things are there. Okay. So does anybody want to share anything on what you found from diode to BJT? Yash was telling me something in the morning. Come and say whatever you have learned. Yeah, if they can see you, so you can come here. The online audience may not be able to see you. Yeah.
Discovery of BJT was in 1947, I believe, at AT&T Bell Labs. So it was a very Nobel Prize winner discovery that they went from a vacuum tube transistor to this solid state transistor. So first BJT was something like punch hole something. So it was like a piece of cake on which gold wires are attached, and they were able to pass that amplify the current. But it was very noisy because of the structure it was. It was what BJTs we look, which are very small. It was like a handful or something. So it is still there preserved in me. So that's what I.
Okay. So does anybody have anything to say about that? Huh? It's your class. I should not be inviting you. You must.
Diode is generally two-terminal device, where BJT is a three-terminal
Correct.
device. And also yesterday we discussed that how if the voltage gets a different, like how the current will vary. That's what we'll see in the BJT. Like if we differ voltage, we see then the current will vary in the different terminal. There we can give it for amplification. We can use it for amplification and all.
Okay, fine. Yeah. Anybody else? Okay, you can keep that somewhere there. So, see, as he said, at least from a historic point of view, that invention was transistor is a Nobel Prize winning kind of a thing. So, it's a very innovative thing. I think a lot of hard work has happened. So, they had vacuum tube transistors, but very huge. Lot of power dissipation. Huge amount of energy. Right? You have to keep heating the coil, electric field, you have to evacuate that. It's fairly complicated to maintain a single transistor. With like 10 transistors, your department will get heated up. So they were trying to come up with some semiconductor equivalents of them. By then, I think they had that. And so they were doing something. That's a story. Again, you can read the technical aspects of what really happened there. My own understanding is not 1947, it's a little earlier than that. Because what happened was, transistors was invented, and the transistor, one of the first uses of the transistor, field uses of the transistor, was as an op amp. How many of you know an operational amplifier? Everybody should know, right? Raise your hand. Okay, thank you. What is inside an op amp? What is inside an op amp? Transistor. Can you be more specific? There will be so many. There could be scores of transistors, hundreds of transistors. Can you be a little more specific? Huh? NP, NP. It can be NMOS, CMOS also. Okay. The input is differential. Op amp's input is differential. So there is a differential input stage inside that. So it is a multi-stage amplifier. The differential input stage will first take the differential input and produce an output. And that output will be, voltage will be amplified by a middle stage. And so the voltage amplification is achieved. Then there will be current or the power will be amplified at the last stage. So at the very minimum, in a very simplified view of op amp, it is a three-stage amplifier. Okay, differential, high voltage gain, and then high current gain. So this is what is the minimal thing that is in an op amp. There can be more improvements at whatever you can do. All that happens. Many things are different there at the basic point of it. So how can you realize a differential amplifier? You need two transistors, correct? So they managed to make a differential amplifier using two transistors and feed that output to another transistor which amplified it further. So they realized an op amp with three transistors. They realized an op amp with 3 transistors. And you know where they used it? The British used it as an input to the radar. Germans were attacking the British. So every night, some 20 to 25 German aeroplanes will come. Those days, the aeroplanes will be very slow. Something like our autos are, autos are very fast. Okay. You can say the Delhi's fatfatis, tap, 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 tap. How many of you have seen the Delhi fatfati? Huh? You know. Okay. So Delhi, you know Delhi, right? So Delhi had a vehicle called fatfati. How many of you have heard about that? Nobody, huh? Few of you. Why it is called fatfati? You make a sound. You'll close your ear. But by then it will move like this. And you'll be emitting a lot of fumes. Okay. That's an old one. Now they have all that CNG and other things. So what I'm saying is the aircrafts are actually very slow. So I used to joke in the class, say that the pilot will shout, "Hey Jack, your cow is going that side." Mind that. They can actually talk. That the height was not so big. Some I'm saying about the many smaller aircrafts. But again, the military aircrafts are faster, but not that faster. See, the technology was much there. But the guns couldn't attack them. So the Germans were coming, attacking, pounding the British towns and going back safely. And once they do it one night, they're emboldened. So next day they come and attack. So the Germans were delivering blows and the Britishers were having sleepless nights and not able to defend themselves. That is when I gathered this happened. What they started doing was they had their radar output and they used this kind of an op-amp and they fed it to their anti-aircraft gun. They managed to feed this op-amp output into their anti-aircraft gun. So earlier what was happening? Somebody was operating the radar and saying, "Oh, it is coming there. Oh, turn. Okay, leftward, rightward." He was giving instructions to the gun. Okay, this angle, that angle, this azimuth and all that kind of stuff. And the other fellow was trying to shoot. Then they were losing. Now, this particular part of the radar was coming into the op-amp and it was amplifying and it was driving the anti-aircraft gun. So they were able to shoot down of 20 aircrafts, maybe 4 or 5 aircrafts. On the next night, maybe even 70-80% of the aircrafts. So in 2-3 nights, the air raids by Germany on Britain stopped. So op-amps saved the British their country. Okay. So this is, all of you may know about the bomb that was dropped in Hiroshima and Nagasaki where they stopped, but this is the another previous one. So this happened during the Second World War. So the transistors must have happened slightly ahead of that. Of course, at a commercial level, companies would have done it later, but military. So many times military things have, derived on this. This is the story that I have heard from my professors. Okay, this is how they did this and come up with it now, op-amp. These are all analog. These are all examples of what we call as analog electronics. Okay, so what we are now going to do is we are now looking at how to do a BJT from what we know. The only thing is I don't want to say that, okay, this is what is a BJT and this is how it functions, as the way it starts from there. So let me marshal what I know. Okay, historical account is one thing. This is another one. So let me say, for my convenience today, I'll take this as NNP. Okay. Let me erase the whole thing. Okay. Because we are going towards an NPN transistor. Okay. Let me write an NP here. So we have understood the depletion layer comes in between. This is what we discussed for a long time yesterday. That is where the depletion layer is. And I know the voltage. This voltage is, okay, let me write it in the current in terms of that. The current through the diode is a function of the voltage. What kind of function? It's an exponential function. So the voltage, and this cannot be voltage, it has to be normalized, right? And that is what is normalized with VT. There can be some constant also, depending on what material is used and all that. But conceptually, you should know that that has to be normalized, and the voltage used to normalize it is the thermal voltage. And that is multiplied by certain scale current called IS. This IS itself can be only, let us say, some 1 milliampere. Even if it is 1 milliampere, this E raised to the power VD by VT. even at 600 millivolt and 25 millivolt, that's about 24. So E raised to the power, that's the diode voltage. IS, it's called scale current. It's just a parameter. It's just a parameter. So this decides how big is your current. So IS itself will be small. That's what I was going to say. E raised to the power VD by VT. Let's say VD is 600 millivolt and VT is 25 millivolt. So 600 by 25 is 24. What is E raised to the power 24? Very large. So IS can be very small, but it is multiplied by something very large, and therefore the diode current is very high. Okay, and that 600 becomes 650, then E raised to the power 24 is becoming E raised to the power 26, and there is a huge rise in the current. Okay, that is what we had seen yesterday. So this is what we are at. Now, what I want to see is, can I create this to the next level? Okay, so what I'm thinking is, let us say I have my N. I have my N, the same N there. And if I apply some voltage between those two, if I apply certain voltage, this is plus minus, and certain V, this will certainly result in some current. Okay, certain electron current in this direction, hole current in the direction. It is going to create that current. So now what I want is, so these are just the voltage terminals, don't get mistaken about that. So this current is what flows in, hole or electron. I don't want that to be lost in the P. I don't want that to be lost in the P. Let me think of the electrons. Lot of electrons are coming in here. And when it go to P, what will happen? They will recombine. So instead of a large P, let me make a narrow P. Let me make a narrow P. Right? So the possibility of combination is less. And this side, let me put again an N, but at a much higher voltage. Sorry, I should. This is at a high voltage. So what is going to happen? All the electrons, hey, come on. They'll get in there and you will get the electron current flowing in this direction. So what should I do? I have that. On this side, I must put a higher voltage so that the electrons get, what happened? Huh? Okay. So I'm going to put somebody here and absorb that. You understand? So what I have done is, I have put someone here. This is reverse biased. This is at a higher potential. It will absorb all the electrons. It will absorb all the electrons. But it should not lose on the way. If people are traveling from point A to point B, right, goods are going. If half the goods are lost on the way, it doesn't help you. So you have to make sure that the goods travel safely. How can they be lost? To recombination. Recombination in P. Make the P small. Make the P small. So from NP, I can make the P small and put an N on the other side and keep that N at a higher voltage. And keep the N at a higher voltage. In that case, the whole current, now this becomes the collector current. You get me? We'll come to that. The idea is where you have to apply your higher voltage there now. So let's now look at, let me clarify on where the terminals are. This is my idea. This is my idea. So let us say I have N, I have P, and I have N. Let me define the terminals. Let me define the terminals. And this is power biased. This is power biased. This is the diode voltage. This is the voltage across a diode. Okay. Earlier I called it VD. Now I will call that as VBE. Now I will call that as VBE. Okay, so I had a lot of electrons moving like this. I had a lot of electrons, and similarly a small number of holes will also be moving in the opposite direction. I'm not talking about that. Now I'm interested that all the electrons pass over there, pass over to the next point. So when they'll pass over their electrons, they'll get attracted if there's a positive potential there. So if I apply a more positive potential here, these electrons will get attracted there. And very few of them will recombine. Very few of them will recombine. And that would finally what will become my base current. Okay, and this fellow will now be called my emitter current, and this fellow will be now called my collector current. Had I had time, I would have asked you to do some exercise in between to arrive at that. Okay, so but still I don't want to start with that. I want you to understand that it is a diode. After that, one more PN junction. That is a reverse connected PN junction. On the other side of the PN junction, you should have higher voltage. Then all the electrons that cross the previous will cross the next PN junction also. Electron flow. That is okay. Yeah, that's correct. I will change the direction of the current here. Maybe I'll change the direction. Okay, let me change the direction of current. Yeah, this would be the direction of current. Here would be the direction of current. So I have to put one more PN junction. So that will be reverse bias, and that is at a higher potential. That will be reverse bias. What it will do is it will suck. The first fellow, the voltage across the first PN junction generates a lot of current. That much current is all safely taken across the next one. To take it safely, you need a higher potential there, and the intermediate fellow has to be low. That is why the base width in a transistor is very low. The base width in a transistor is very low. So if you actually look at books, they will show you the picture like that, right? Like we saw that yesterday, no? Like you had that. Now you will have some more line like this. So this may be your N, this may be your P, and this may be your N. This could be your transistor structure. Of course, I'm not showing all the terminals where that is coming there. So it will very narrow and it will cross. So I have leveraged my idea from diode to go forward to the transistor. So what is the current relationship now? The same VBE decides the current. So what current? The collector current or emitter current, both are almost the same. So it would be the collector, because all the electrons are absorbed here. So the same thing happens to the whole current, which I'm not talking on that direction. Maybe I can also write there's a smaller amount of whole current here. Okay, that also goes in this direction. Okay, so what will be the relationship now? The entire current that passes through that is passing the next one. So that is the collector current now. So this collector current is now an exponential function of whom? VBE. And the argument of exponent should be a number this is at its simplest the current versus voltage relationship of a transistor. But this is a transistor in what mode? Active mode. The emitter base is forward biased, the collector base is reverse biased, and that is what is active mode. That is where it acts as an amplifier. How does it act as an amplifier? You can see a small change in VBE creates a large change in E raised to the power VBE by VT, and therefore IC. Small change in VBE can create a large change in that. So that is why it can become an amplifier. Okay. So now we'll move to the next point. So there are two things I can do, 2-3 things. One is to see how you make an amplifier, or the other one is to go complete the characteristics. Okay, so I think I'll go and complete the characteristics for you. Now, I'm looking at understanding the characteristics of the current versus voltage. Now, this is a 3-terminal device, so I have a problem. But IC and IE are more or less equal, so I take IC. And this voltage, VCE are the main power terminals. VCE are the main power terminals. I want to come up with this characteristic. Okay, right. So what was the previous equation I had? IC is equal to IS times exponential of VBE by VT. There is no VCE at all. So what does it mean? No relationship. It is independent of VCE. Independent of VCE in certain range. What is that certain range? In this active mode. It is operating in active mode. So VCE is going to be VBE plus VCB. How much is your VBE? It is forward biased. VBE is forward biased. So the VBE itself will be something like 0.7 volt. Right? The VBE itself will be that. And then you are having another reverse biased BC. So this fellow is operating on this side. We are operating on the right side of this line. Why? VB is 0.7. VCB adds to that. It's reverse biased. C is positive with respect to B. So that could be anything. 1 volt, 2 volt, 3 volt, 5 volt, 8 volt. It will work. So that is your active region. And in this region, as Yash said, it is independent of VCE. So independent of VCE means what? This fellow will look like a horizontal line. Let VCE change. It will be constant. What does that depend upon? According to this expression, it depends on VBE. So if I have higher VBE, it will be like that. If I have lower VBE, it will be like this. If I have lower VBE, this may be 650. This may be 675. If I take 700, it may be like that. Okay. So these are part of the characteristics. Now, what is this mode? We are now in the active mode. This is in the active mode. That is where it works as an amplifier. Okay. And in analog electronics, you use the transistor in the active mode. In power electronics, you don't use the transistor in the active mode. You use it as an on-off switching device. It will go through the active mode when you are having a switching transition, or when there is a fault, it will go into that. These are all the times it will go into the active mode. Okay. So this is now what I'm going to have. So part of the characteristics are clear, right? And when VB is very small, what will happen? Current is practically zero. This will be here. So for very low VBE, this is very, very low, that you are going to have. The current will be very low. So it is the so-called off state. This is low VBE. For very low VBE, your current is going to be zero. That is what is your off state. And remember, in the off state, it can be blocking significant voltage also. And that is very important for you. So it will be somewhere on the horizontal line. It will be blocking it. So now what I want to do is, I want to go further and see what happens here. Let me redraw that. So I have a lot of electron current flowing like this, and this is forward biased. Previously, what was happening? I was reverse biasing here. When will I go here? When when I forward bias that. So let us say previously I was having it forward biased. This was forward biased. Let's say this is at 10 volts. So you are well inside this. I gradually go on reducing this 10 volts. I gradually go on reducing. Say it is from 1 volt. And finally it becomes even 0. What will happen? You will be somewhere at this point. You will be somewhere at that point. Now, let us say I go in the other direction. I make it minus 0.1 volt. What is minus 0.1 volt? What is minus 0.1 volt? I'm forward biasing. I'm forward biasing the second PN junction. Until now, the second PN junction was reverse bias. But 0.1 volt will not produce any significant change. So the second fellow won't inject any current. The second fellow will still remain open. Will still remain open. And therefore, it will be like this. And I make it minus 0.2. Same story will continue. Same story will continue. Why? It is forward biased, but the voltage is very small. Finally, let us say I'm forward biasing by minus 0.4 volt. It's funny that it is negative because I started with the other polarity. Now what happens? By the time it comes to minus 0.4 volt, you are 400 millivolt. Correct? So 400 by 25 is a significant number. A significant current starts flowing. This current is in the opposite direction. This current is in the opposite direction. Because it is forward biased. The electrons from there are flowing in here. And because of that, what happens? This fellow falls. This fellow falls. And when that 0.4 becomes 0.45, falls further. And when it becomes 0.5 or so, it comes. Okay. This is how the characteristic of that looks like this. So let me write these are all at different VBE1. This is VBE1, this is VBE2, right? This is VBE3. Normally you will see that written as IB, but I have drawn it against VBE because our expressions are really against that. So second one also the same thing will happen. If I am operating with VBE2 also, as I am forward biasing collector base, it will go like this. Here also collector base will go like this. So what have we looked at? Back-to-back diode, and with forward biased CB junction, we are able to deal the active mode. That is where the transistor BJT becomes an amplifier. Correct? And now the second PN junction, I'm not reverse biasing, I'm forward biasing. In that case, what happens? That opposes and the current actually comes lower. And this is what you call as the saturation mode. They call that as saturation mode. You see that this is almost a vertical line. You see that this is almost a vertical line. And this is what they call as VCE SAT. Okay, they call this as VCE SAT. This goes by the name VCE SAT. That will be typically some 0.25 volt or so. So you can look at this particular portion. If you can actually read through Smith or any such book. Smith is what I know and I would recommend. So you can certainly, you'll get a good idea of that. We have to do things even faster than that here. Okay, but that is to say how you move from one to the other. From diode, we move to the active region, and from the active region, we have now moved to saturation. Correct? Okay. So when we reverse bias the PN, that is going to be one is there is a reverse active mode. We will not worry about that. Otherwise, it will be off state. Otherwise, it will be a off state. Okay, so that is how it is. So let me go back to this active mode and look at something else that happens there for you to complete the picture. Again, remember, these are representative drawings, okay, for us to understand. N, P, N. Now, in the active mode, once again, I have this picture. I have this fellow reverse biased. So this fellow is emitter, and you can see the name emitter is very meaningful because it emits electrons. It emits electrons, and it is very much tied to the vacuum electrons. And this fellow collects electrons. Okay, that is why the name collector. You can see all the names are very closely tied to vacuum electronics. So this fellow maybe only 0.7 volt. This fellow may be 0.7 volt. This fellow may be some 10 volt. So it's a huge reverse bias. When reverse bias, what happens to the depletion layer? Only if it becomes stout, it can block a voltage. Only if it becomes stout, it can block a voltage. That is why during forward conduction, the depletion layer will be very narrow. It doesn't have to be stout. But when it is off, it is blocking a huge voltage. You can block the huge voltage only if it becomes stout. So see, these are all the intuition that you can get. If the voltage has to be high, you know that the triangle of that electric field density has to have a bigger base, and that is why it has to be. Okay, so these are all some reasons why you do this now. In this case, what happens something, if this depletion layer becomes big, correct? This is the depletion layer of the collector base junction. So if this depletion layer increases, the effective base width reduces. The effective, because base is so thin. The base is so thin, if the depletion layer becomes big, collector base, the base reduces. As a result, the base current you have slightly reduces, or the recombination reduces. The recombination reduces. When the recombination reduces, the overall current there is greater. When the recombination reduces, the current seen at the output is greater. And so, this is not a flat curve, but goes on increasing like this. That goes on increasing like that. This is still in the active mode when the reverse bias voltage is quite high. When the reverse bias voltage is quite high. Okay, is it clear? So what will happen if the reverse bias voltage increases even further? Huh? Very small, and finally it will break. Finally it will break down. So if you go very far from this, it will finally break down. It will finally break down. And the current will shoot up. That is breakdown. The diode breakdown, you would have seen people drawing it the lower side. Here it is in the top right corner. Because the breaking diode is the collector base diode. The collector base diode is what is breaking down. Okay. So this is the breakdown. You won't go near that. And this is what is there. And this, it's a straight line. If you go on projecting the straight line, this fellow will go and meet the horizontal axis somewhere there. This fellow will go and meet the horizontal axis somewhere there. This phenomenon was discovered by a gentleman called Early. E-A-R-L-Y, Early. I don't know whether he used to come to class early. So Early. And so the term is called Early effect. Okay. The term is called Early effect. Which term? This rising like that. And this fellow will go and join somewhere there, and that voltage is called early voltage. So this line has a small slope, right? You go on extending it, this line will go and cut the x-axis, negative x-axis. That voltage is early voltage, minus VA. That's early voltage. I cannot draw, I have to draw that in a different scale. I have to draw it on the wall. Okay. So the effect of this early voltage is, earlier what was it? It was independent. Earlier, current was independent of VCE. Now slightly dependent on VCE. So, and earlier the slope was entirely zero. For a large change in V, I was not changing. Now, for change in V, I is changing. So there is certain output resistance. So, earlier it was like a current source. Now this fellow is like a current source. Okay. That fellow is like current source with some output resistance, the parallel resistance. Clear? That is the picture that you will get in a actual amplifier. Okay, so this is what you do now, and this is the early effect that comes in there now. So they account for the early effect by adding something here. Okay, to this they'll add something. Okay, there's a small term that is added. I'm not getting into the term that involves VDS. It's a resistance there. You can see that. So I'm just stopping there. The expression that I have written is ignoring early effect. So with early effect, there will be another term getting added to that. That term will have VCE. That term will have VCE. So VCE multiplied by some conductance term. That is what is correct. That is what you will get there. Okay. So I'll stop to complete my BJT characteristic. Okay. Any questions on this? So what happens is, whenever there is any VBE, there is always IB flowing here. It is impossible that IB is 0. Okay. And so when IB always flows, you can always characterize IB and IC also. And then different betas can be given. Then that will become a current gain. Yes, because one way I would say is, if the current is 0, it will not work. If the current is 0, that will not work. Okay, that's a philosophical question there. When you really come there, it comes from a diode. It comes a VBE. In fact, there used to be people agitated. Oh, why are you writing that? They are always used to writing IC as IB times beta. Okay, now if you look at IC and IB are similar. IC is a function of VBE by VT. IB is also a function of VBE by VT. IB is also, that's another diode current. That is also a function of AC by VT. So this IC, if it is 100 milliampere, that IB will be 1 milliampere. And so you can express them as a ratio. Both of them are very similar functions, and typically you can express them as a ratio, and then it becomes convenient to express. Yeah, the MOSFET, the voltage above the threshold is what makes it conduct. So here I would imagine that the current has to flow to a certain extent. Even though if you are applying VBE, VBE of 0.1 volt, 0.2 volt are not doing anything. And unlike MOSFET, we are not able to say a threshold. We are not saying that VB has to be greater than this. But at some point, current starts rising. That is what you are calling as your cut-in voltage or something. So the current starts rising. So after that, it works. So this is a question that I am also not too clear on why they say. But then the adverse effect of calling it as a current control device, makes people miss the point entirely that it is also dependent on VB. But you can see that we have arrived at this point very logically. Okay. The point that further is, I don't have time to discuss. If you write IB also is a similar function, exponential function of VB by VT, and they are roughly proportional. IC and IB are roughly proportional, and that proportionality constant is what you call as current gain. And then now you are saying you are looking at it as an amplifier, right? So what was the quantity of interest for you? Collector current is of interest for you. You want the transistor to give so much collector current, signal current, so much. So you can say that if I have to get that much signal current, this should be my base current from beta. You get my point? I need 100 milliampere, and the data sheet is saying beta is 100. So I should try and inject 1 milliampere. So let me see how I can inject 1 milliampere into the base. So from a practical point of view of using it as an op-amp, that is what they do. This is at least my understanding of why they say that. No. Let me understand that. This is a high amount of current, right? If you are okay, there is a very high amount of current flowing there. This is your IE. This is your IC. And this is going to be your IV. So, yeah. Correct. Hmm. 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 Correct. Hmm. 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 Correct. That is what is called reverse active. That is what is called reverse active. I mentioned that in a passing, but reverse active is not a recommended thing. So I would have shown you previously. Is it possible for me to go to a previous slide? So NPN, anything can be called emitter or anything can be called collector. I would say this is emitter based collector. You may say this is emitter based collector. But the difficulty is these two PN junctions are not exactly identical. These two PN junctions are not exactly identical. It is not a symmetrical device. They'll say it is not a symmetrical device, whereas MOSFET is a symmetrical device. MOSFET at some level you can transfer diode and source. When they deal with MOSFETs in the IC, right, when they make hundreds of transistors, okay, anything can be called source, anything can be called drain. That's not the case in power MOSFET, because in power MOSFET we do some additional connection and call something as drain and something as source. So when you are building a power converter, don't interchange that, but inside that is a symmetric device. Here it is an asymmetric device. So this goes into what is called as a reverse active mode. And in the reverse active mode, the characteristics are very poor. It cannot conduct as much it can conduct. Okay, so those kind of things are there. If you look at that reverse active, that would be a third quadrant operation. That would be a third quadrant operation. That's not an encouraged one. Okay, so I'm also not getting into that now. But that's something that you can certainly look into that. Okay, clear. Yeah. Yeah. Okay. So this is now fine, right? We have the BJT characteristics. Let's quickly move on to the MOSFET characteristics, which will look similar, but not same. Which will look similar, but not same. So when I deal with students, if I ask about 20 students to draw BJT characteristics and MOSFET characteristics, 10, 12 of them, 50, 60% of them easily draw the same set of characteristics. Okay. Now, what do you think? Are they same or are they different in your knowledge? But I'm told that BJT is not taught to you, right? Did you study BJT in your subject? No, you did not study. So the confusion doesn't arise. Okay. So I take back the question. Since you don't know, we will not there now. But you know a MOSFET, correct? So I request one of you to come and draw the structure of a MOSFET. Okay, let's start with that. So who can come and draw? Are you going to volunteer or I have to volunteer someone? One of you please draw that. You come and draw. Forgotten. So, 3 of you can go and try. You go. I think you would like to try. Or maybe him. You want to try. Okay, go. 2. No, that is okay. I want three different pictures there. 2 of you, and I'll pick someone else. Who can be someone else? Yeah? Maybe this lady. You can go and draw. Draw a structure of a MOSFET as you understand. Okay. You can draw on the left portion, or divide the board left, middle, and center. Let us see how you can work together. If you are going to see what is drawing and then reproduce that, then you draw whatever you know. Yeah, you with your finger you can draw. Middle you can draw. Kanna, Asha should slightly move to the right so she has some space. Yeah. Doesn't work, okay. Okay, wait for him to finish. Then you start, he'll do next, and you do third. Wait. It is getting confused and multiple fingers are there. I didn't know that. It doesn't allow parallel processing. We are always testing it to the next level. In the board, I used to say, do all that. See? Hmm. Yes, madam.
Sir was asking the same question. You said that reverse active is not, it's because that the width is also different.
They are very different.
That's only a thing that.
It is an asymmetric device. This I can take. What is your name? That boy who drew now? David. Okay. And what is the girl's name? Mehek. 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 That is the first name or last name? Okay.
All these things will come in your exam.
The third thing,
Whose exam? Which for which year? But what about the third and fourth year students? Whatever you think you draw. Over. Okay. Thank you, Mahek. Let this man finish. Is that right? Where are the terminals? This is what MOSFET is this? N channel. N channel or P channel MOSFET? N channel MOSFET. You forgot the doping. Okay. Why is it that you're not able to draw? If you say that I studied some years back, I studied this decades back. Why is it that you're not able to draw? What is the reason? What is the reason? Memory has faded. Correct? So why is it memory dependent? See, you have to understand and correct yourself in a manner that this won't happen again. You understand? Why you are not able to draw today is not the big question. Will you be able to draw this 20 years later? That's the question. You will need this, something from this. Okay? Don't think that I am doing this uselessly. I have no time to do. Oh, what is power electronics in this? Power electronics devices, they'll fail if your switching is not proper. They will not work. Ask anybody who knows ABC of power electronics. If they don't switch properly, they won't work, fail. Most failures happen during switching. And you have to understand switching transitions. Switching transitions cannot be understood unless you know the characteristics of the device reasonably well. And the characteristic of the device does not come and jump from somewhere. They come from the structure and physics of the device. You understand? Okay. Yeah. So, Shashwat is only a little confused. if it's N channel MOSFET, okay, it is to be by inversion. N channel will get formed by inverting a P channel. So Shashwat must correct this as P. If I correct this as P, right? Only if I correct this as P, an N channel will be formed here. And if this is P, this fellow will not be P. This will be N. This will also be N. And not just N. Like Sriraj was asking yesterday, it will be N plus. Okay. This is again reproduction. This is again reproduction. But is this reasonably correct now? I want the class to confirm. Can you say this is correct? Reasonably? You have, huh? What is missing? Oxide is missing. Where is the oxide? You come and draw that here. So one issue is Shashwat was trying to show the third dimension. So he was getting lost in the two. You can stick to a two dimension. We will understand that the third dimension normal to the board, it is similar. Okay. So that you don't have that burden of drawing. Very good. Very good. Very nice. Okay, and where is the N channel getting formed? Draw that. Yeah, draw that. Okay. This is very close to what you can actually get in a book. The only things that you will see different are, if this is a dielectric, this fellow will also probably go and cover the whole thing, and then they may have shown some terminals here to connect to them. This is the only differences that you would have seen, the metals to connect them. This is a very accurate picture. Okay. The trouble here, one of the issues, why is that? Why? So you know why, what is happening now? Does anybody know what happens now? Once I have given the picture, I can probably say a few things. What is happening now when formed? When I applied voltage in the gate, higher than the threshold, the channel will get formed. When the channel gets formed, then there's conduction between this N plus well and this N plus well. One of them is called drain and the one of them is called source. That will, depending upon whichever voltage, it's part of an external circuit. D and S are part of a different circuit. So current will flow through that. So this is one. Let us keep this as such. So let me try to understand how I would want to do that. Okay. I want to create a MOSFET. So MOSFET stands for what? MOSFET. It is metal oxide, silicon or semiconductor, okay, this is, so it is a transistor. So what do you mean by transistor? Let's see if we have understood the BJT now. What do you mean by a transistor? I'll start the discussion. A 3-terminal device. Okay. What else? 2 back-to-back junctions. That is BJT. Not a transistor. That is a bipolar junction transistor. If you have to realize a transistor using that, it is a specific transistor called bipolar junction transistor. In general, what is a transistor? Transition from one state to another. Okay, I heat up water, it will become steam. transitions from one state to another. Therefore, water is transistor. Huh? Can be used as an amplifier. Okay, good. So transistor again, trans means across. Okay, trans-Pacific means across Pacific. Transatlantic is across Atlantic. And I think it's trans-resistor. It comes from there. Okay, you can look into the history. So words are always interesting. Why it came up, I leave that to you. So BJT had 3. What was the attribute? Somebody said an amplifier. Well, I will add that. It's a 3-terminal device which can be used as an amplifier. I'll add your input. Then if it has to work as an amplifier, what should it satisfy? Anything else? Anything else that BJT was satisfying? Less amount of the signal voltage change is causing a large change in current. Okay, voltage where, current where? Which voltage, which current? Base emitter voltage and collector current. So you should be able to control the voltage at 2 terminals and influence the current at the 3rd terminal. That's the beauty. It should have 3-terminal device. It should be capable of work as an amplifier. If it should work as an amplifier, what will happen now in this, as a consequence or whatever related one is, the voltage across 2 of the terminals will determine the current through the 3rd terminal. So similarly in a MOSFET, the gate to source voltage is what determines the current through the drain. The way may be different, but the same way base to emitter voltage is determining the collector current, the gate to source also will determine the drain current. How? Exact relationship will be different. Okay, so that's transistor. That is transistor. And now what do you mean by field effect transistor? These are all reasons why you should understand electric field better. Okay, field effect transistor means what? Some field is being applied. As a result of the field, this transistor's operation, comes into operation. Okay, this field, is it electric field or magnetic field? Electric field. Why is it electric field? Because you are going to use a voltage between gate and source to create that. So it's going to be electric field. Okay, it's not by current flowing through some conductor, but it is voltage being applied somewhere. So it is going to be electric field. So now this brings you to electric field. Clear? Okay. Now somehow I have to, again this session gets a little longer than what I intended, but I think we will miss something if we don't do this. So what is a transistor now? 3-terminal device. And it's capable of being used as an amplifier, but it can be used as switch also. Okay, amplifier is only one of its avatar or one of its roles, and the current at one of its terminals will be controlled by the voltage across 2 other terminals. That's the beauty. And now there we realize as back to back, here we are saying we'll use field to affect that. So we'll somehow create an electric field, and the electric field will cause the basic operation of the transistor. That is how we are now trying to see. So that is one side. Now I don't know where I start from. Somehow it should come to a field, but I know that I'm going to be working with a semiconductor. I know I can work with a semiconductor. So it can be P or N type. Let me choose P. Let me choose P. So if this is a P-type semiconductor, by applying electric field on it, can I create some change? What can I do? What can I not do? You can, for example, electric field can always cause current. Why? J is equal to sigma E. Okay, electric field can cause current when you have a conducting path. When you have a conducting path, the trouble is you have to create a conducting path. So here, what do I mean by creating the transistor operation? I have to create a conducting path by applying electric field. I have to create a conducting path by applying an electric field. Can I create? Can I create? Where can I create? Obviously, I can't create an electric field in the middle of this. Create a path in the middle of this by applying an electric field. I can apply the electric field somewhere from some side, and I can create a path some side, right? Let me say I want to create a conducting path here, very close to the top. It is very close to the top. Can I create that conducting path by applying an electric field? What should I do? What kind of path it must be? What is the field I should do? How can I create this path? Let me say what path I should create. This is P. I want to create an N-type conducting path. I want to create a N-type conducting path. Can I do that? If I somehow attract negative charges. How can I attract negative charges? By applying a positive voltage. And that means there is an electric field has to apply. An electric field, what always happens when you draw the electric field, we draw several figures yesterday. I have a positive, we have a negative. It starts from positive, goes into negative, right? This is how the electric field lines are. This is how. Now, if this fellow, I want it N, means I want a lot of negative charges to come here. So if I apply the electric field lines will terminate here. The electric field lines will terminate here. So let me choose a different color here. Where is the color here? Here. Okay. Now, they have to start from somewhere. And they can terminate here. I can apply. If I can create such an electric field, I can create this channel. All the field lines will come and terminate there. And where will they start from? Positive charge. Where will they start from? Positive charge. So how can I do this? How can I do this? If I have a semiconductor, I have some insulating dielectric layer. If I have a dielectric layer and I have a metal on top. So if I apply, I have to have positive charge everywhere. So I'm creating this plate. That plate is full of positive charge. So positive charges are there, negative charges are here. Therefore, the electric field is like this. Okay. So what is that I'm doing? I'm trying to create an N channel in a P substrate. How can I create that? Through field. It has to be created only the side only, because the field can be applied from the side only. So if it is N channel from there, all the field lines have to terminate at the N channel. They have to originate wherever. They have to originate at some positive side. So there I have to put some insulator there, dielectric there. And the other side of the dielectric I have to apply plus, and therefore this side of the dielectric will be minus. Okay, this is how I can create that. This is how I can create it. Something like this, the whole thing is there. I'm able to apply, put some semiconductor here and apply a potential. So there is field and it creates a channel there. Okay, so this is how a channel can be created. And now this is metal and this is oxide. This is oxide. This is oxide. So I can create, and there is semiconductor below this. Okay, I can create a channel. If the field is there, channel gets created. If the field is not there, channel is gone. If the field is stronger, the channel becomes bigger. And that is what it is called enhancement. Charges accumulating there. Well, I'm not a man really to answer. So it's a very, very thin region. This end that is drawn there, okay, it's too thin to be measured as material thicknesses. Like in machine, the air gap, right? Air gap can never be represented correctly, because in a machine, you will have an air gap of 0.5 mm, where the machine dimensions will be, let's say, tens of centimeters. So you cannot draw to correct scale. You cannot draw to correct scale. If I draw 0.5 mm as this gap, then 50 centimeter will be bigger than the size of my board. The same way, the MOSFET channel is too very thin. The MOSFET channel is too very thin. And this channel is essentially accumulation of negative charges. It is accumulation of negative charges. So I would encourage you on creating that. When you apply that, they will say that there is something called accumulation, and then there is called inversion. There are 2-3 stages that happens prior to this. Okay, entirely there is P there. After some voltage is applied, some of them start accumulating, and after that, the amount of the density. See why it is like this. It is not that holes are there and electrons are not there. The holes are much higher than electrons. Here what will happen when you start going on increasing the field, first they will be same, right? Holes will be much more dominant than electron. Later electrons will go on getting attracted in a very thin layer. This is microscopic. In a very thin layer they will keep getting attracted. So after some time it will become neutral. After some time it will become neutral. The holes and the negative charge will be similar. After a while, then the negative charges there will start dominating. And that is the stage they call inversion. That is the stage they call inversion. So there the P-type substrate has been inverted in a very, very thin region. It has been inverted. Okay. Right. All right. So now, this is how I create using a field. If I apply a field, channel comes. If I don't apply, it doesn't come. The field has to be strong enough. The field has to be strong enough. That is why they say it has to be greater than threshold voltage. It has to be greater than threshold voltage. Threshold voltage is that level. It creates that level of electric field. It creates a channel there. Prior to that, channel doesn't get formed. And only when you have that inversion happening and there is sufficient conductivity through them, it gets there. Okay. In all the previous cases, whenever we studied P and N, that's material there. And they are much bigger in dimensions compared to this. Here you have only created a layer through your field effect. Okay. So inversion is one of the stages. After inversion, it happens now. Right? So part of the picture is clear. So this is a channel. The channel will get formed, channel will flow. But is the channel useful? You build a road, nobody uses. You build a library, nobody uses. What is the point? Nobody reads. You build a lab, nobody works. No point, right? If you create a channel, someone should flow. Who will flow? Current. Right? Current has to flow from something to something. And what is a transistor? Sometimes when you want, current should flow. When you don't want, current should not flow. That is the on-off of a transistor. Okay. So I'm going to take this a little farther. No. Okay. So I'm going to create this channel. And what will flow through this channel? Negative charges only will flow through this channel. Negative charges will only flow through the channel. So I need a dabba. Where will the negative channels come? Here you have got them by attracting them. Okay. It is something like, somebody is already poor, but you have snatched away, whatever. This piece fellow had very, very few negative charges. Some of those also you have attracted them. And that is only to create the path, not for everything to conduct. So you bring someone who is very rich in N here. This is N plus. This is N plus, where you have a very high doping rate of N. Here again, this is N plus. Very high doping rate. So the left side fellow can give more charges. His concentration won't change. The right side fellow can give more or accept. His concentration doesn't change. See what is called the earth. You know the term called earthing, right? The 3-pin plug, there's a third pin that is longer. That will go and make the connection first. What does it do? It connects everywhere and finally lands in the ground. It provides earthing. So what is the beauty of earth? Any amount of charge you inject onto that, its potential won't change. You inject or take away charges, its own potential won't change. What you try to do in power converters, many times, as a small patch of copper is made to behave like earth, as ground. And that is very difficult. It cannot be zero potential. So it will keep jumping. That is the challenge that you handle. One of the challenges in a power electronic converter. So this is an earth. Earth can take any amount of charge and do this. So same way, if I come up with an N plus region, the N plus region can give any amount of negative charge or can accept any amount of negative charge without its own concentration changing quickly. So that is why there is N plus on both sides. You understand? So now what I have to do, I only have to put the terminals here. Let's say I'll put some terminal here and call this as drain. I'll call one of them as source. Let's say I'll call this source. I'll call this fellow as drain. This is my picture. This is how the information I store. Okay. So we'll get into how this is structure. This is called lateral structure. Okay. The trouble here, as you have already noticed, what I told in response to Sriraj's question, the channel is very thin. Means what? That is where conduction is going to happen. Conduction is going to happen through a very narrow channel. Its main dimension is what is called W in the other direction. It's W multiplied by the channel height. W is significant. But this channel height is very, very small. So cannot conduct high current. Cannot have very high current. Power MOSFETs will not be like this. Power MOSFETs will have something called vertical structure. Power MOSFET. But this is your starting point. So this is called lateral MOSFET. This structure is called lateral structure. Okay. Yeah. So you can look at how a power MOSFET looks later as you go on there now. Okay. Now, yeah, we'll quickly break for tea and come back. What would be the next task? We will derive the IV for MOSFET. Okay. Yeah, not more. Please let me know if there are any questions and comments. Probably have to display that there, maybe. But what is shared. Yeah. Yes, please. Anything from online audience? Okay, I can see the camera there. Yeah. Can you share the comments there, Vajanti madam? Okay. The chat window. Okay. Yeah, Professor Tariq ul Islam. Yeah, he said yes. Okay. Yeah, anybody who has a question can unmute and go ahead, please. Just inform Shashwat, we're just waiting for Alok. Is there any problem in unmuting? So 10 others, who are the 10 others? Can you click on that and see the details? Okay. So Anjana Ethirajan, yeah. So can anybody answer? You are able to hear us? Is there any problem with unmuting? Divya, Neil, Srivastav, Nishad, Sagar, Saurabh Chandra, Sharwari, Shivrudra Swami, Sridhar Joshi. Can you just unmute and speak? And if you have any questions, please let us know. Yes, you.
No, sir.
Hello.
Yes. Hello, sir.
Okay. Just want to be sure that you're able to hear us and everything.
Yeah, yes, sir.
Very good. Any questions, sir?
No, sir, no.
Thank you very much. So anybody online audience, okay, I'm not keeping an eye on the window, but others are. So if there's any question, just please raise your hand. Yeah, we'll talk to you. Because I'm not able to see you, I'm not able to directly talk to you. Yeah. So Professor Tariq, you have any question? Please. Tariqul.
Yes, I'm audible, sir.
Go ahead, sir.
Actually, sir, when explaining about this channel inversion, can you say that when you apply the positive potential at the gate terminal, it will attract electrons to the channel, and as a result, channel conductivity is gradually going to increase. Can you explain this way also?
Sir, I think the audio was little loud and then they have reduced now. Can you repeat your question, sir? Yeah.
Okay, just a minute, sir. My question is that, sir, when you explain that when you apply the gate potential is positive with respect to substrate, then it can attract the electrons to the channel, and as a result, it is going to increase the channel conductivity.
Yes, correct.
So, can you explain that way also?
Yeah, you can certainly. Yeah, certainly.
I mean, this is what my query is, that, sir. Thank you, sir.
Yeah. Actually, that subject of the channel formation is an involved subject. Okay. The channel formation is not usually discussed in electronic basic level textbooks, but there are more semiconductor oriented textbooks where the emphasis on semiconductor is quite high. Okay. So they have chapters on MOSFET, metal oxide silicon capacitor. So the material scientists, when they actually make any dielectric, the way they test is actually they make a so-called MOSFET. So they make a metal oxide silicon capacitor, semiconductor capacitor out of that and test that out. So there are involved processes, and the inversion is the last stage, as I said. Okay, accumulation precedes that. Okay, accumulation, depletion, inversion. I think something like that. So there are multiple stages. These are all in the dynamics of how that gets formed. So we are usually not concerned about them, because we are now looking at the IV characteristic. During the IV characteristic, we are at the steady state. Okay, so we are not typically talking of how the channel forms or the dynamics of the channel getting formed. But all these accumulation, there will be depletion, accumulation, inversion, all these multiple stages are there. So one could refer to them for that. It is only after the inversion happens, the channel gets formed. So If you apply higher voltage, the electric field gets stronger, and when the electric field gets stronger, it attracts more number of charges, and the strength becomes increases more. That is why the conduction in a MOSFET is proportional to VGS minus VT. It is proportional to VGS minus VT. Until VT, nothing. After VGS, if VGS minus VT is 1 volt, it will have some conductivity. If VGS minus VT is 2 volt, it will be roughly twice. Yeah. What happened, Shashwat? Come, Alok. Where is he? Go ahead. Yeah, we'll resume that. Go ahead. You can just hold a microphone for you. So Alok will now derive the IV characteristic of MOSFET for us. You go on to that and share that window. And yeah, he doesn't have to use this. No, he can use the finger. Yeah, go ahead. If you are speaking, you have to speak on the mic. They'll load the correct page, right? So now we have asked Alok Yadav to derive. We are now into IV characteristic of the MOSFET. Just before the tea break, we looked at the MOSFET structure. See, this is the workshop. Unfortunately, we cannot have detailed discussions. This is a learning. We are now trying to look at important topics, how to connect, such kind of things like that. Because the curriculum should be basically a 2-3 semester curriculum for power electronics, machines, and drives. So we are trying to see what can be the important highlights, what are the important topics. Okay, covering all the topics in 1.5 hours, 2 hours, anything. And so some of the messages until now is, for example, devices like electric fields are very important in device. How do you do that? How do you review electric fields, right? How do you use vector calculus? How are vectors and scalars related? So many of those were already things coming up there. But you already had that file also. Wait for a while. Yeah. Go ahead. Okay, you start with that. Because when you want to derive, sometimes you know what to derive. But yeah. That's your next finger touching. Yeah. Yes. The next finger shouldn't touch. Which is I. Which is ID. What are the mark the labels? Label the axis. Okay. Is this correct? No, this is incorrect. I can guess what happened. You just opened the book, saw the curve, tried to register an image and reproduce the image. Okay, I'll take every step as a positive step. No, stand down. If we are not able to derive, we'll see what is the problem in deriving. Why is it we are not able to derive? You understand my point? 4 plus 3, if you are not able to add, we'll see why we are not. So 4 in the mind, 3 in my finger, 5, 6, 7, we'll do that. Because it's a teaching learning workshop. It's not that IV characteristics have never been derived in the world. It is for us to learn how to derive that, how to use that. You understand? Okay, clear. Now the class is clear that your curve is incorrect. Can you correct it? Can you correct it? Or you can start from deriving. You can start from deriving. Okay. Write down IV characteristic on the right hand side. Say wherever IV characteristic you write down. We have to know what is the problem. And this is again not for packed food. This is not about packed food. This is for you to learn how to learn. This is not I divided by V. That I slash V will give an impression that it is I divided by V. Okay, so write your IV properly. Now this I means which current, V means which voltage. I means which current, V means which voltage. Which current and which voltage, firstly. Specify the current. There are multiple currents and multiple voltages here. Which current, which voltage? And I. Which I? Okay. Let us say that is also possible. It is possible to get ID and VGS, but that won't look like this. Right now, people were talking, right? If it is VGS, up to V threshold, current will be 0. That is not reflected there. And above V threshold only, current will rise. Above V threshold, current will go on increasing. It will never saturate. Oh, sorry. That is a straight line. After that, it increases, correct, but that will not increase like a straight line. Okay, I'll ask you another question. BJT, what was the voltage we derived? What was against what? You were there in the previous session, no? That is where the talk came from. In BJT, what was the y-axis? What was the horizontal axis? Write it down next to that. I, was it collector current? When you attended the BJT session, what was the y-axis? Collector current. Choose the pen option. Okay. No. Don't have to strike down anything. Okay, fine. I wanted you to choose a different color. That is why I said go to pen. Go to pen, and there's a different color will come. Choose red color. Okay. Now, what was the y-axis when we did the BJT? What was the y-axis? I, C. What was the x-axis when we did the BJT? Write it with the same color. V what? What was that V? Voltage has to be between two terminals. Voltage has to be between two terminals. Can be one terminal. That is not what we derived. That is not what we drew at the end. So I want you to analyze what was your problem with this. Okay, because learning is an activity that is done at the individual level. If I am not able to learn, I should see why I am not able to learn. Raghavendra tells me something I am not able to understand. Why? I have to understand that. You understand? Okay. So, but we'll continue. I'm not going to leave this. We're going to continue. Okay? There may be some issues that we may have to address, identify and address. Okay. And if it is not VB, what other voltage will be there? What is the next possibility? This is an important question for everyone to consider. If it is not VBE, what other voltage you can consider? VCE. So write VCE. Now, what is the significance of IC versus VCE? Why at all is it necessary for us? Why at all is necessary for us?
Please tell about how much IT will be there when they are increasing the.
Mostly, it may not be anybody applying voltage there. To my knowledge, voltages are applied at so-called input terminals in a circuit. You don't take any voltage source and apply any voltage between collector and emitter. You may have an amplifier. Amplifier may have an input. You may have a power supply. It will have an input. You will be applying your voltage at those terminals. You will never apply the voltages between the two. Voltage may get applied because of the circuit connection and whatever inputs given. So why do you think this is important? Okay, let us say if we are not able to move in one direction, it's not the end of the world. There are infinite directions. If we did IC versus VCE for BJT, what should it be for MOSFET? Now you change the color of the ink. Now change the color of the ink. Correct. Now instead of IC, what is equivalent to IC in the MOSFET? Yeah. How many MTech students are here? 5 of you. How many are there in your class? Are all MTech students here? You are second year. But how many students are there totally? MTech? First and second year together is? What is that equivalent, Kanna? What is that? What is the equivalent? ID. What should be the equivalent to VCE? What should be equivalent to VCE? Where are the, see, there are ERP, there are okay, industry people. How many are there on campus? Where are they? Are they having classes? Okay, inform them that it's an important session today in their interest. Okay, then it is up to them. This is my job. I've come this. I'm going this additional mile to say this. Yeah. You can head back, but you have to understand why. I wanted to start from a different point. It is VDS, right? How do we go about deriving this? How do we go about deriving? What is the starting point for the derivation? Let us not know the complete journey. At least I should know if I go to Goa to Bangalore, I should buy a train ticket or a flight ticket. At least that I should know. Right? This is a brief explanation on how it operates or the principle of operation. This is not about derivation of I versus V. Do you understand the difference? When I want to derive I versus V, what is the starting point? We understand the structure. We understand the operation. After that, we have come. What is the starting point? Just like I said, if I have to go to Bangalore, I should know that I should take a flight or a train. What is that I should know? What is the starting point? Again, everyone need not do it the same way. But everyone should have a valid way. The valid way, there should be a valid first step. You understand? Mine and Raghavendra's and Shashwat's may be different. But approach should be correct. What is the starting point? Where do I start from? You should know about? Okay, V threshold is given. Let us say. There is something called V threshold. That is understood. Next. Sorry, again, schedule is going off, but I think we have to correct certain things. There's no point in my going and telling this is how you go out and derive. When you don't know, when you can't adequately recognize the difference between operation and derivation of a particular relationship. Qualitative explanation of operation and a quantitative derivation of relationship. You understand? And I don't want, it's all right if you don't derive, but I want to know what is the first step. Where will you start from? Where will you start from? That is only common sense. There should be a series of steps. You have to help yourself. You can take help from someone. That voltage difference, your gate source is there.
And after so that electrons will there is already voltage will calculate all.
How will you calculate? How will you calculate? Okay, continue this exercise. Go back to your seat. Continue this exercise. Thank you for this. Yeah. Now I want someone else to come and start off the first step. Someone can come and start off the first step. We have known the structure. We have known the operation. So what is the first step that you have to do now? What is the first step? Maybe the 0th step, put down the structure correctly. Put down the relevant portion of the structure correctly. Okay. Who can do that? Can you do that? Yeah. David, right? What's your name? Huh? Yes. Who is David? That man was somewhere there. Vanished. No, not David. He said something else. Huh? David. Ah, see. David only. There was one David there who is now. Ah, okay. Okay, fine. So reproduce the structure with the relevant detail. Reproduce the structure with a relevant detail. Now, Kanna. So this is the structure reproduced. Go ahead. Go ahead. Okay. There is no, that is not J is equal to sigma E. That is not J is equal to sigma E. Correct, Kanna? What you are drawing, that is not related to. Okay, go ahead. Go ahead. Now, I said one thing. Reproduce the structure with relevant detail. Reproduce the structure with relevant detail. Does it make sense? Are you able to understand this word? Yes? Language is clear? Purpose is clear? Seems logical? Do that. There must be a channel. That is an important missing detail. In fact, the channel is not an additional detail now. The channel is the detail now. The channel is, so this is the 0th level. The first level is not this. The first level is the channel with adequate detail. First, draw the channel with adequate detail. Do that, Kanna. When you draw that. Draw the channel. Now, can you do it, Alok? What is the meaning of this? You draw it on your paper. Whenever I ask something, it's not necessary that you have to do that. Please do that in your sheet. He has indicated the channel, but what did I say? Relevant detail. The channel is the main detail. Channel is the main detail. The aspects of the channel as are relevant to this derivation should come out there. Current has to flow through the channel, correct. First, how the channel looks like, you have to put in that there's something. Okay. Thanks for, yeah, you can go back. I want someone else to come and represent the channel now. Who will do that? Shashwat, you want to do that? You have done that here? That's your channel, no? You draw the channel. The focus is now on the channel. Go draw that. So whenever Shashwat has to do, Kirti also has to do some exercise. But that's all right. Yeah. So we will not worry about the big picture. We will now worry about a certain portion of that that is relevant. We know that that is connected here, this is connected here, that substrate is here, etc. Right? Let us focus on the relevant portion. Because this is where a lot of issues are there. Yes. Yes. I think, but he's only redrawing that, no? What is he indicating now? So let us first understand the channel is very thin. It is so thin that you cannot express that to the scale. It is thinner than your line. It is thinner than the line that you can draw in the actual scale. First, let us understand that. Okay. Next, what does he say about the channel? The channel is straight and there is uniform. That is very good. You say R0 or low VDS. This is, what is the situation now? VGS is greater than V threshold. Write down. VGS is greater than V threshold. And low VDS. You understand? Write down. Only VGS is greater than V threshold. This is what is the starting point. It's not less. If it is less, the channel won't get formed. You draw the conditions. This is not the end, it is the beginning. Please understand that. If it is equal, the channel will hardly be visible. It will be hardly visible. It's greater, but VDS is okay. Right, low there. When VDS is 0, I is 0. I don't have to derive the characteristic. You understand? It makes it irrelevant. Yes? So VDS is low. Now I will ask you how low is low. This low is fact. If you write VDS is 0, I know ID is 0 and VDS is 0. I don't know. It's going to help me calculate ID versus VDS characteristic. So he is saying VDS is low. Correct. Now how low is low? Is it 1 volt, 2 volt, 10 volt, 20 volt? It is with respect to what? Which threshold? VGS minus V threshold. So VDS is much lower than VGS. So change your English statement low VDS into a mathematical statement. VDS is much lower. VDS is much lower than VGS minus V threshold. So what are you saying? You're acknowledging that VDS also has an impact on the shape of the channel. But its impact at this point in time is not there. Under that condition, I am trying to understand. Okay. It is much lower, you are not writing. VGS minus V threshold, put that in a bracket. Has he written much less than? I am not able to read. And VGS greater than V threshold. Both are the conditions there. Okay. Okay. Let us say in this condition, it's also possible to finish. It's not the complete situation. It is only one scenario. Okay. And what will be the current versus voltage during this scenario? Any idea you can think of how to derive or something? This is not yet the general one. Do you know how to do that? Scenario is correct. You have depicted the channel, except that the channel is shown bloated. Please remember that. The channel is too thin to be shown. Okay. It's not really a material that is manufactured. It is something created by that. And the region becomes richer and richer or bigger, whatever, as VGS minus V threshold. So can you relate ID and VDS at this point? What is your idea? Kanna, relating what is to be related to what? ID. Can you relate ID to anything else now? Okay, so unfortunately, yes, thank you very much. So now I'm giving you two options. One option is I want you to say how will ID and VDS be related here? What is the condition? VG is greater than V threshold and VDS is much smaller than VGS minus V threshold. Question I'm asking you is, I want to know whether you want to do the derivation, which is deriving IV for a particular scenario, or you want to look at a more general scenario. Which one you want? Huh? You want to go towards a more general scenario. So that, okay. Are you saying this because you are not aware of how to do ID versus VDS? If you are not aware of that and therefore you are postponing the problem, that problem will be bigger for you. The more general case of the channel is more complex. You get me? So consciously take the decision. Okay, ID versus VDS. Where is ID flowing? It is flowing through the channel. Correct? And it is being driven by the voltage across VDS. Please remember that we are not applying the voltage there, but there is an effective voltage appears there. What do you think is the relation between the ID and VDS? How will they be related? This ID and VDS. How do you think they will be related? Something like a resistor. This must be a conductance term. This must be a conductance term. At this stage, it is a resistor with uniform conductivity. It is a resistor with a uniform conductivity. Okay. So that will depend on what? How highly conductive it is, it will depend on what? VGS minus V threshold. So ID is certainly proportional to VDS. ID is because it's a conductor. It's a simple channel. VDS doubles, ID should double. So ID is proportional to VDS. Making sense, Sriraj? Next, I will worry about what is the constant of proportionality. The constant of proportionality should have conductance dimension. Okay, that will depend on the conductivity of the channel. And the conductivity of the channel will depend upon VGS minus V threshold. It will depend on. So at the next level of refinement, I will write that this is proportional to VGS minus VT into VDS. Okay. Not the complete this thing, but I've gone one step closer to that. Okay. So if you complete that, it is very relevant in power electronics. There's a term called RDS on. When the MOSFET is on, there is a drain to source RDS on. What is that RDS on? This constant of proportionality. The reciprocal of that is RDS on. So it's a very important parameter. It is a very important parameter. You can go and attend to the book and see what they are writing here. That will depend on the conductivity of the channel. That will depend on VGS minus VT. You can see how much charges, how rich are the charges in lay sense to come up with that. So, but what I want to at least say now at this point is, we are looking at a situation, in the situation that Shashwat has suggested. Okay, this is ID, this is VDS. But this VDS is much lower than VGS minus, sorry, this is is much lower than VGS minus V threshold. Okay. For this, it's a straight line. Is that? And if VGS minus VT increases, if VGS minus VT decreases, okay, we have at least moved off the block. We have at least moved off the block. Create. How did we move off the block? Wide scenarios are there. We took one scenario and we took the simplest scenario. And we have come up with the nature of relationship, not the exact relationship. The constant of proportionality is not yet done. The constant of proportionality is not yet done. But we know the constant of proportionality is also proportional to VGS minus YT and the nature is known. Clear? That is why in MOSFET, if you operate with a higher value of VGS, this is higher VGS. The drop is low. What happened? Is it from here? Hello? Hello? You're able to hear me? Yeah. Something fell outside, huh? Or something fell out. Yeah. Okay. So we have moved, but we don't know the exact value of constant, but that is proportional. So we have moved some distance. You can go further, but now what I know, at least I know how it is rising. Okay. I will go to in the interest of time, I'll go to more general case. I'll go to more general case. So what do you have to do in a more general case? What happens? What is more general now than what he said? He said VGS minus VT, right? This VGS minus VT must be greater than 0. Otherwise, channel will not get formed. Channel will not get formed. What is more important, earlier when he drew, he said VDS is much lower than VGS minus VT. I am simply saying it is lower than VGS minus VT. I am saying it is lower than that. VGS minus VT can be 5 volt. My VDS is 4 volt. It is lower. Much lower means if VGS minus VT is 5, my VDS is 0.5, 0.3. You get that? In this situation, VDS cannot be ignored. Okay. Now this is my N plus. This is my N plus. And now what happens to my channel? What happens to my channel? What happens to my channel? Very good. The channel looks like this. It's a straight line. The channel looks like that. This is what we believe. This is what is given in book. This is what we remember. And this is what we believe is right. So we have put that in. So now let us try to see why it is like that. Why is it like that? Why is it like that? When they are saying opposite means what? See, there is no direction for a scalar quantity. If a vector quantity has direction, you can say these two are opposite. Charge density. Why is the charge density decreasing? See, I will not say charge density decreasing. Okay, I will say so-called channel height is decreasing. Okay, I'll be a little safer. Why is it decreasing? This potential of source and this potential of drain, this is now source now, this is now drain. They themselves are not at equal potentials. They themselves are not at equal potentials, but the gate is at certain potential. Okay. Normally, you make sure that the channel covers the whole gap there. Many of you might draw lower than that. So, this is where I have applied my VGS. This is where I have applied my VGS. So, whatever is my gate voltage with respect to source, whatever my gate voltage with respect to drain, they are different. They are different. This may be 5 volt, That may be 1 volt, 2 volt, 3 volt. When they are different, will the channel be uniform? Cannot be uniform. Then we will say where the channel height is going to be high. It's going to be high when the voltage difference is high between gate and source. Okay, let us say this side is 5 volt difference. This side, let us say it is maybe 2 volt or 3 volt difference for now. So what is going to determine this height is nothing but how much charge. The same capacitance is there. What is the capacitance? This is the capacitance. The capacitance is very identical whether I take here or there. That is, I can take some point here, I can take some point here. The capacitances there are same. Because the same dielectric, same thickness. The same dielectric, same thickness. The dielectric above them. The capacitance is same. Voltage is different. So what I'm trying to say is, there is an elemental capacitance. There is an elemental capacitance. So let me say this is an elemental capacitance. This is an elemental capacitance. This is another elemental capacitance. The capacitances are same. I should not say elemental capacitance. The width of the capacitance is actually elemental. Those two capacitances are same, but the voltage across them are different. Their voltage across them are different. If the voltage across them are different, the charge has to be different. The charge has to be. If the charge is different, the channel height is different. Clear? We are constructing the more general case. We are constructing the more general case. This picture is what I was intending to say as a picture having the relevant detail. That shows the channel. That shows the channel is bigger on one side, smaller on the other side. You get that? So now what do I do? I've understood something. So can I be more specific on how much charge is there? How much is this capacitance? How much is capacitance? We're not talking of complete capacitance. The capacitance has certain permittivity. What is capacitance? Epsilon A by D. Correct? So let us say the thickness is Tox. This is oxide layer thickness. So this is capacitance per unit area. This is capacitance per unit area. So let's call this COX. But remember, this is not capacitance. This is capacitance per unit area. So we have put something mathematically there. Then what happens to the charge? So there is some small charge dq here, some small charge dq in this. Okay, what is this? This is dx. This is dx. I'm trying to see how much charge is there in dx. You understand? There's a complete channel. The channel starts from x is equal to 0 and goes till x is equal to L. This side of the channel is x is equal to 0. This side of the channel is x is equal to L. I'm considering some dx in between. I want to see how much charge is stored in dx. How much charge will be there? This is capacitance per unit area and I have to make this into complete capacitance and I have to look at the voltage. Charge is the product of that. What would be the complete capacitance? This is dx and there is another dimension. That other dimension will be W. So W times dx will be the capacitance value. This has to be multiplied by some voltage. This has to be multiplied by some voltage. What is that voltage? No. VGS minus VT minus, if I call that as V of X. There is a voltage from this end to that end. That is what I'm calling V of X, minus V of X. Remember, every problem in life can be handled in a logical manner. Every problem in life can be handled in a logical manner. You must first understand what the problem is. You may not understand. You have to think calmly. You may become part of the problem. If you become part of the problem, you cannot solve that. Okay? We are learning how to learn. And this is applicable not only to our education, it is applicable to life, career, and many other things too, with modifications. Here, this is all extremely objective. There is a mix of objectivity and subjectivity. Yet, you can always be reasonable, rational, and take very good decisions. So, what is this right-hand side fellow? Capacitance per unit area and multiplied by the area of the capacitance, and then this is that. So, this is dq. This is dq. That is why I waited for you, Sriraj. I want to see what is the effective voltage that is creating the charge across the capacitor. Did I write 5 volt here? Did I write 3 volt here? What is the meaning? I am having VGS minus VT. My VGS minus VT is 5 volt. And my VDS is 2 volt. My VDS is 2 volt. First thing somebody told, the drain and source are not at the same potential. The drain and source. In a capacitor, you will have 2 parallel plate capacitor. That will be at one potential, this will be at potential. This is a funny parallel plate capacitor. One plate is at the same potential, the other plate, different lengths of the plate are at different potentials. You understand? The top is the positive plate of your capacitor. The bottom is the negative plate of your capacitor. Okay? It is all drawn exaggerated. This layer is much thinner than your insulating dielectric. Okay? Because we cannot show that we are showing it like that. If I have to draw an ant, I cannot draw the size, right? I can scale. And not only that problem, in certain devices, some parameters too very small compared to the rest of them, like air gap in a machine. Similarly, the channel here. Okay. So this is a funny parallel plate capacitor. The top capacitor is the same potential. The top capacitor is at the same plate is at the plate potential. The bottom, this side is at 5 volt, this side is at 3 volt. Middle will be 4 volt. Why? This voltage drop is because of some current flowing there, roughly. Because of some current flowing there. Okay. So let us say I consider a point, somewhere arbitrary point X, and Vx is the drop from here to there by virtue of some current flowing from here to there. So at that point, what is the voltage across this capacitor? VGS minus VT minus V of X. Is it clear? Why? This is source. Very good. Very good. So he is looking at which one should be drain and which one should be source. This caution is very important. Most of you drew drain here and source there. I drew source here and drain there. When I drew, I knew that I was writing my source to the left and drain to the right. I knew, you look at the previous slides, they would have written drain here and source there. But I look at source here and drain here. Okay. I knew I was doing that. The next point that is valid is, which side is big, which side is small. Given that I have written this as source, I have written this as drain. Which side is small, which side is big. What is the effective voltage that causes the channel close to source? VGS minus V threshold. VGS minus V threshold. Now VGS minus V threshold is 5 volt. Let us take V threshold is 5. VGS is 10. So VGS minus V threshold is what, 5. Okay, let me write down the numbers for clarity. Let me imagine VGS is 10 volt. V threshold is 5 volt. Sometimes I'm writing threshold as VT, VTH, but don't mind that. And let us say VDS is 2 volt. Okay, so effective voltage is what is VGS minus V threshold. The effective voltage is what is really causing how conductive or how big or whatever is your channel is. Lower than that, it doesn't exist. Okay, so it is VGS minus V threshold. That is 5 volt. The elemental capacitance towards the source is charged with 5 volt. Elemental capacitance towards the drain is charged with only 3 volt. Clear? And somewhere in between, that would be between that. It may be 4.8, 4.7, it may be 3.2, 3.3. So we don't know what. Therefore, we are defining something called VFX. Therefore, we are defining something called VFX. Starting from x is equal to 0 to that point, there is a certain drop. This is by virtue of current. This current is J is equal to sigma E current. This current is J equal to sigma E current. E does not have all the E when it is applied in an electric conductor, it creates current density. When E is applied in an insulator, it creates electric field, no current. Okay, E need not have the same effect. The first E is E in an insulator, which creates an electric field, and that is the field effect. As the effect of the field, channel is crossed. There is another E because of the voltage between D and S. Because of the voltage between D and S. When voltages are different and they are separated by some distance, there is certain gradient. There is some rate of change of voltage along the path. And that is what is called electric field. And that E is the E driving the current. Okay, that E is J is equal to sigma E. That E times sigma of the channel will give you the J. So please be aware of two effects of E. And both the effects are playing here. Both the effects are, it is like a funny parallel plate capacitor where they have some voltage. Second plate is conducting from this end to that end. You understand my point? This is my top plate. This is my bottom plate. Bottom plate won't get created unless I apply my top plate voltage. This will not be there. When I apply voltage, this will come there. And current flows from my elbow to finger. Current actually flows from my elbow to finger. It's a funny capacitor. And therefore, the effective is different. And therefore, the charge across the capacitance in this elemental length dx, Sri Raj, is VGS minus VT minus VFX. Okay. That has to be multiplied by the capacitance, epsilon naught by Tx into WDx. So this is my dq. Clear to everybody? Yes? Raise your hands if it's clear. You're spending a little longer, but I want you to be clear. Raise your hands if it's clear. Alok, not clear to you? Then you have to raise. Now, what happened? I have to undo something. No, all that is gone, no? Undo. I think I should be saving. Huh? Oh, I pressed highlighter by mistake. Is there anything that can make it erase? Okay, fine. All right, okay. Don't worry. Don't worry. Clear that up. So let me now do that systematically. Okay. So I have a dielectric sitting here, epsilon ox by T ox. That is the capacitance per unit area. That dielectric is uniform in its dimensions. Okay. It is capacitance per unit area. It is capacitance per unit area. So now I have given this condition. VGS is 10 volt, V threshold is 5 volt, VDS is 2 volt. I am taking this condition. So under this condition, I have 5 volt overdrive here. I have only 3 volt gate overdrive on this side. And if I look at something in between, I'm looking at an elemental length dx. I'm looking at an elemental length dx. Starting from 0 to dx, I have a potential drop of Vfx. I have a potential drop of Vfx. This Vfx is because of the E field that is driving this current. And you will do this now. So how much is the charge that is held in the dx? How much is the charge held in the dx? That I am going to call as dq, because it is in an elemental length, and that is epsilon oxide by T oxide. This is capacitance per unit area, and I have to multiply by the area, that is W dx. That is, and I have to multiply this by the voltage. What is that I should write here? VGS minus VT minus VFX, sorry. Clear? So what do I have? I have come some distance. I have not covered the entire distance. So let me say what distance I have come and what is the gap. What do I have from here? I have dq by dx. Last time I thought I will strike that out and bring that here. Now I will write that. Now dq by dx is epsilon naught Tx W times this whole voltage. Okay. This is dq by dx. What do we want? Current. What is current? dq by dt. That is dq by dt. So what is the gap? I have dq by dx. I should come up with dx by dt. What is dx by dt? There are some charges moving in my channel. It is their speed. How fast they will move? How fast they will move? Depends on the electric field. Which electric field? The electric field along the channel, not the normal electric field, normal to the channel, which has created the channel, along the channel. And okay, what is that electric field? What is that electric field? Electric field is gradient of voltage. The electric field is gradient of voltage. So, dV by dx. And this I have to multiply by some factor to get my speed. What is my speed? Dx by dt. And there is some proportionality constant. There is some proportionality constant. This, they call that as mobility. They call this as mobility. So we have written dq by dx. We have written dx by dt. If you multiply by the 2, you will get I. Multiply the 2. I'm not going to write anything on this board, but I want you to multiply and say what happens. If you multiply the 2, what will happen? So we are heading to current, right? So this is where you have to come to. You constructed a simple condition, then you constructed a more general condition. The simple condition, you figured out how the relationship is, and you prepared yourself for the more complex condition. And the more complex condition you discussed for a long time. Remember that. There's been a long discussion on the channel. Why the channel is tapered? Why is it on this side? Why is it on that side? You remember? And it is only after that you need that. Then that condition you are representing it mathematically. You are recognizing that in every elemental length dx, the charge is different. Correct. So I comes in terms of dV by dx. Okay, you're going to multiply the two. It's very simple. It is only mu n comes in here and becomes dV by dx. Okay, let me go to the next slide. You remember the figure, right? I will not do that. So now this I, see, I am focusing on the principles. So I'm not worrying about conventions and this and that, right? Those details you take care of. Now this I, what was it coming out to? Some epsilon ox by T ox, and there was W, and there was mu n. All these are constants. All these are constants for a particular MOSFET. You can probably call them K, K and something. Okay. And this gets multiplied by what? VGS minus VT. Okay. You don't have to really recall. You know VGS minus VT is the effective gate voltage. And you have this drop, VFX. The more you understand, the burden of memory and recall is lower on you. And dV by dx. Okay, now I is available in terms of dV by dx. I have to integrate this. So what I'm doing is, this is actually IDX. This is IDX. And this is dV. Okay. So you're ready to do an integration and come up with a final answer. And if I integrate here, it's with respect to x. What are the limits of x? X is equal to 0 to L. And what are the limits here? At x is equal to 0, V of x is 0. At x is equal to 0, V of x is 0. dV is your variable. V of x is 0. At x is equal to L, V of x is radius. Great. Now, this is x. If you apply the limits, it is I times L. I times L. Correct? This side is constant. Epsilon naught x, Tx, W, N. And what happens here? This VGS minus VT is a constant that gets multiplied by V. The second is V. That becomes V square by 2. That becomes V square by 2. So there is a V term and there is a V square by 2. And the V term, when I multiply by that, I am going to get VGS minus VT. This is multiplied by V, and I apply the limit, it will be VDS. And V becomes V square by 2, and that becomes minus VDS square by 2. Believe me, I have never done this in this detail anywhere. Okay, I'll only tell them this is what it is, this is the step, you go do that. But today I thought we'll break that. So what happens now, L? What happens to L? So this W by L is the size of the transistor. Mu1 is the mobility there. Epsilon ox Tx depends on how good dielectric you have chosen. So it is like this. Okay, clear now? If you have understood this, okay, if you are able to reproduce, it is a necessary condition that will show that you have understood. But that is not a sufficient condition that you have understood. You have to do something similar. You have to do something similar and something different applying this. Then you can be sure that you have done. You understand what I'm saying? In the class, I used to say, if I have taught you two concepts, it doesn't mean that you have learned and you have understood that. Only if you're able to apply that. You have to digest and you have to show it somewhere. That is only a proof that you have understood. Until then, it could well be your imagination that you have understood. Let us be very clear. Outsiders don't fool us. It is our mind that fools us more often. It is our mind that fools us more often. It is our mind that makes us less clear. It is not that people outside are wearing some kankan and taken a vow and to get you confused. You are getting confused because of your mind. You have to clear up your thinking process. You understand? So how did we come to this step? Is now clear to you? So what are all the steps we did here? What are all the steps we did here? We read the structure. Let us start from that. Okay. So from the structure, what did we do? We came up with the relevant portion. We came up with a relevant portion of the structure and considered a simple condition. Under a simple, what was the simple condition? Voltage greater than threshold, but VDS is much lower than VGS minus VT. So Shashwat drew that. We got a feel for the problem for that region. Then what did we do? We constructed a bigger condition. Then for this, we have gone ahead. After we created that, what did we do? We observed how the system was. We made use of our idea of capacitance. We made use of our idea of capacitance. We made use of our idea of relation between charge in a capacitance and the voltage across the capacitance. We recognize that the voltages, the effective voltages are different at different points in the channel. We express that mathematically. And we mixed everything to a point where we could say in certain elemental length of the channel, this much is the charge. We were able to say that. When we were able to say that, then we recognized that we could do dq by dx. We could do dq by dx. Then what we wanted? I, that is dq by dt. Then task is easy. What is missing? dx by dt. You understood what is missing? dx by dt. Right? What is dx by dt? Drift speed. The speed at which the charges moves. So what is it proportional to? The electric field that is driving the current through the channel. That is dv by dx. And we came up. We mixed the two. Then we thanked our 11th standard maths teacher and integrated. And finally, we came up with a solution. Again, this is valid for what region? This is valid for what region? VGS greater than V threshold and VDS less than or equal to VGS minus VT. Don't lose sight of this. No expression is derived that is universally applicable. Even the great laws like Newton's law is applicable only at some levels. When the masses are significant and the speeds are low. When the mass becomes subatomic kind of masses, or the speeds become of the order of light, 1/10 of the speed of light or something, Newton's law doesn't hold. When the particle becomes quantum, Newtonian mechanics is taken over by quantum mechanics. So there is no thing that you derive is absolute. Okay, we stop there. So the only other thing that we now need to do, so this is the limit. Okay, and I'll complete the drawing here. What kind of curve is this? This is I, is now I'll call this ID. ID with VDS and VDS square. What is the curve? Second degree polynomial. So what will be the corresponding curve? Parabola. Is it a upward parabola or an inverted parabola? Inverted parabola. Why? This is minus. It is an inverted parabola. At VDS is equal to 0, I is also 0. So this parabola goes through 0. So this is ID, this is VDS. Okay, this parabola goes through 0, and this is where you are having VGS minus VT. This is where you are having VGS minus VT. This is valid only for this. What was the earlier expression you did? When VDS is much lower than VGS minus VT. There it is a straight line. There you can see it is a straight line. The straight line has become a parabola, and here it is 0. After this point, what happens? It chokes. That is, the channel becomes like this. This is at x is equal to 0. This is at x is equal to L. Even if you increase VDS beyond that, it will not increase further. So the conductivity is not going to increase further. This becomes a horizontal line. This becomes a horizontal line. So somebody asked a question. The textbooks are a little confusing. So the textbooks call this as the triode region. I mean, they have the right reasons, and they call this as saturation. They call this as the saturation. They call this saturation because the diode current is saturating there. The diode current is saturating there. So somebody asked me this question. In BJT, the terminology is different. Okay. Very similar. IC is flat, and that is proportional to VBE. In the other case, it is proportional to VGS minus VT the whole square. It is VGS minus VT. That's also like a current source. And here, if you go, you can't reduce this voltage. This voltage will be more or less like a vertical line. You will be driving a higher current. That is, that base current you said, if you take 100, what is 100? IC by IB. You will take IC by IB at something like 10 to drive it harder. This will still be something like 2.5 volts. This will be something like 2 to 2.5 volts, and this is what is called VCE SAT. So in some sense, you can't reduce the VCE voltage below that level. You cannot reduce the VCE below that level. So there is a saturation. Who is hitting the limit? VCE, not on the higher side, but at the lower side. So this is called saturation region. This is called saturation in the BJT terminology. Okay, but you can always go by that it is active, right? Where it is acts as an amplifier. Where this acts as an amplifier. In that other region, it is a switch on state. If you go by that, there is no confusion. Okay, so this is the characteristic. And now if I go back here, if I have to draw other value of VGS, what will I get? It will go and saturate somewhere else. So I will actually get some kind of a parabolic relationship here. So these kind of curves will go here. These are for different values of VGS. So VGS minus, this is proportional to VGS minus VT the whole square. So this is also like a current source. This is also like a current source. And what happens is, let me hope that I don't lose anything now. How do I change the color now? If I have to press this again, I don't want to lose this again. Huh? I have to go to pen. Okay. Okay. I'll go to, okay. No, I'll color change. I'll change to, let's say, blue. Okay. Thankfully, I've done that. Okay, I'll save that. Very good. As PD, whichever way you want to save. How do you want to save? Huh? PDF. Okay, it is saved. Now you have to give a name. Just save now, you can save it. Okay. Do it. Okay. We'll finish that later. That's all. The matter will be done. Now, because VDS goes much higher than VGS minus VT, a small change happens. The small change happens is the channel reduces. Not by so much. The channel doesn't reduce by so much. This is some delta L. This is some, not by so much. I have exaggerated and shown you. And the channel stops there. It doesn't mean they are not conducting. It doesn't mean they are not conducting. What is happening is they are flowing here and there's still a very high electric field. There's a very high electric field because the drain voltage is much, much greater than VGS minus V threshold and it attracts. It attracts. So the channel length reduces and W by L comes at the bottom. So this actually becomes L minus delta L. This becomes, so L minus delta L is L into 1 minus delta L by L. So it is less than 1 and therefore the current increases. Therefore the current increases. So this is slightly, it will increase. Very similar to early effect. Very similar to early effect. Again, if you project that backward, all these curves will go and meet the horizontal axis at some point, minus VA or something, equivalent to the early voltage. So these are all the additional details that we wanted to look at. So this is your IV characteristics of all of them, going together. We did this because Post lunch, we are going to use these IV characteristics to see how a MOSFET switches in a power converter. Once we understand that, I think that is analog, digital, and some small differences are there. What is coming there? Okay, in analog, many times it will be a resistive load to the transistor. In digital, the load on one transistor will be another transistor. The load on one transistor will be another transistor. In the case of power electronic, the load on transistor will be an inductive load. Will be an inductive load. And because of this, there will be some changes. Let's just understand that. I'm not so much concerned about the analog and digital, but I want you to be clear on that particular one. But I want you to be aware of that firstly, and then you can get more and more clearer as you go on. That's not an issue, right? And then power electronic, when that switching happens, we are going to use this to find out how the switching transition happens. Yeah, we'll stop. Yeah. 5 minus 3 is 2. 5 minus 3 is 2. No. It is what is the effective voltage that is holding the charge. Here the entire voltage comes there. Here this minus VDS goes there. The drain is at higher potential. That is VGS minus V threshold. So it is effectively that this elemental thing is holding charge equivalent to 5 volt. Here it is holding a charge equal to only 3 volt. Afternoon we'll do that. Remind me that. Stop now. I've got one or two questions. Yes, very clear. Right? Let's take this kind of picture. And let's see. We can very close to it. Yes. So only dimensions are there. So back to back. Because they are back to back. And when they make MOSFETs, hundreds of MOSFETs, they're nice. So one thing that you might want to know, because nowadays many electronic engineers actually go to most of our graduates are electronic engineers. When you do something in the semiconductor, nicely, then when you do discrete components, for example, when you're doing it outside in a very space, you can take an inverter, you can make an inverter. But inside an IC, you don't want to have it. That's right. What's the requirement? Capacity. You can keep capacity on discrete components outside. IC, capacity will take a lot of space. But there's some epsilon. Unless there's significant weight, capacity will take a lot of. So some things are limited, and very difficult areas are current source in discrete components. You have to say sometimes, but they can be done very well, and that they see that they are working at that once. Some people are different. So when they do IC, there are MOSFETs. Okay, it can be very important. Is that symmetric areas? Instead of this DNS, it will change, right? Well, there will be MOSFETs happening, but they teach MOSFET the following understand. Exactly this thing. So, as somebody pointed out earlier, there is a source. There is a substrate. The substrate and the source are connected together. Substrate and the source are connected together. Therefore, you cannot indicate source and drain. That is our source, that is our drain. That is why you get MOSFETs. So, now where will the P injection get from? Where will the P injection get from? This is N plus, right? And this is P. So, there has to be some in around them. Now, which one? These two are shorted, there is no voltage left. But this P to N plus is blocking voltage. That P to N plus is blocking voltage. So, the depletion layer is going to be formed. And you see there is a light doping. Is that light doping? The light doping can take up. Okay. This is not the structure when you do. Right? This is indicated the lateral vertical structure. So we only have one source and drain. What we do is we say this whole thing is a drain. This whole thing is a drain. And that's my gate. That's my gate. And here is my channel. Channel of my driving right? Hello. Yes or no? This is could be a ring structure. There could be a ring structure. Or the part that we can make donut. The contact is like that. Substance get created there. Okay. So this side, then this is your gate. This is your gate. This is your gate. Therefore, substrates single one, not that. And current will actually run. And the interest regions are going to be very good. That will be your most your there is a much indication of power. You get that? There is a source. Okay. On the day, you are not able to imagine and believe it. The lateral MOSFET is like what is going on. Right? What is going on before water, right? Like small level of course. That is lateral. Very, very thin line. Here, you imagine I am a well. Am I? Well. I have a wall around me. Correct? Like this where things. And well has a ring. You have a parallel wall. That is where the gates are. That is where the gates are. So, water can flow from all the sides. If you take hole to that wall, the parallel wall, what level? Water will flow through the parallel wall and come to the side walls of the well. Get me? Not here? Yes. Gate is like a ring. The gate is what allows. The water is like a well collecting water. This is accessible. So I have a gate around that. And the gate, when I apply the field, that will create a channel. That will create a channel. So the channel is at the surface of the land. That is where the channel is. The channel is formed, water can flow from multiple directions. Understand? It's a flow, water can flow in only one direction. And this channel is formed by applying an electric field, normal means. That is lateral MOSFET. And in the vertical MOSFET, imagine like it's a well, the bottom of the well is that, right? And you have the rim of the well, right? And that is where the gates are. And where the gates are. When the gates are not enabled, nothing can flow into the well. When the gates are enabled, water can flow to the entire well from all sides. Right? Structure is vertical. Flow is. So this you can look at as vertical structure. I just attempted to give you, something like that. You can look at what's called vertical MOSFET. You will be able to read more about that. Many data sheets, they also tell you a representative picture of how the gates activity are aspect. Okay. So I just talked about that derivation as body. Substrate is connected to S. So this is P. There's a P and there's a P, so NP, back to back. Okay. And the substrate is connected to the source. Okay. Substrate and source is this is P. That is your body. That is your body. Clear? No. Source to substrate is a diode. But that is shorted. So substrate to drain is one diode. That is what is called. So with this we move on to cover this. I only want to look at the transitions. So circuit analysis is something that we will be doing. There is no problem, the circuit is resistive. If there is no problem, the circuit is LNCR. The resistive algebra, RLCR there, with differential equations. Right? We'll get that. So one problem that I want to address is we are sometimes stuck when our circuit is like this. If I write greater than is 5 volts, okay, whatever you can call that. Now, if I written R1 and R2, you would have very easily written the current. You would have very easily written the current. You would have said that I is equal to R1 plus R2. Then write them very quickly. No? No? I think it is. Let me draw the other one. Let me draw the other one. Let's say, I say R1, I say R2. This is one branch. Very easily I will say I is equal to this is by R1. What is really the circuit equation? The A is same. IR1 plus IR2. Because I plus R1 plus R2, I is equal to this is by R1 plus R2. That's how that. What do you do here? What do you do here? You still have to write KVL. You still have to write KVL. What is the KVL here? IR. So you get IR plus VD is equal to there IR1 plus IR2 is IR2. Voltage conversion is IR2. That's a very clear link. Now, here is VD. How do we solve that? How do we solve that? That's clear. I've just said about the necessary network. I am diverted. Okay? Yes, sir. How do we solve? How do we solve? VD is to be sometimes. This is why the characteristics becomes important. Okay, this really is a function of ID. You have some characteristics like this. ID. This two-terminal device has a simple relationship. What is the relationship? V2 is equal to I times R2. This is V2. Whereas here, it's not that easy to write. This is what you have to recognize. Now, this is where the characteristic becomes important. How is this to be solved? How is this to be solved? So, what we do is, that's the terminal. Okay. What are the terminal relationships here? I is equal to VCC minus VD by R. What does it represent? The terminal equation of the circuit. Terminal equation of the circuit. The second one I have is I is a function of V. What is that? That is a characteristic. I have to. That is why the characteristic. So how do you do that? Now, let me read that. I is f of t is known to me. What is VCC minus VD by R? This is my second equation. My second equation. What is the equation? Right. Right. What is the other equation? It is VCC minus V by R. So initial value is VCC by R. The mean is 0. Right? That will be a line equation. Slope is minus 1 by R. So what is the solution? So equation 1 is nothing but a quantity that relates an equation that relates the terminal quantities of the circuit divided by nonlinear element. That is what we call as very simple circuit. The moment I put a nonlinear element, right? This is what is called this norm. Have you heard load line? This is load line. What is blue here? What are looking this? Because that's so heavy. Yes. Connecting, not connecting. You know about load line, right? Is it that you know that load line was like this? Huh? What are you saying? Huh? You will know load line. So let me go to something else. So the problem is here view, we are having a resistive network. The resistive network we are simply using on nonlinear electronic circuit. So there are tricks to solve this. There are tricks to solve that. What will be the trick to solve? Somebody will say, I will consider this as piecewise linear elements. Okay, this will be operating point will be slightly different. Not exactly there. Operating point ratios will be slightly different. That's all. That is all. So you approximate the characteristic. Okay. So now this I take IV versus GD. This represents the operation of the diode over a complete range of power tag. Okay. So this I'm going to introduce a term. It's called that large signal model. Okay. This is what we call as a large signal model. And this is basically a piecewise approximation. This is a piecewise approximation of the large signal. This is a piecewise approximation of large signal. So what are we doing here? What is the small signal model? So I just wanted to introduce this idea of large signal and small signal right here. So let me say ID is equal to IS exponential of dy by sure. This is a large signal of the diode. The first one when it is connected. It is valid for the entire range of operation. It is valid for the entire range of operation. So sometimes you might want it at a particular operating point. This ID, okay. You are operating at this point. You are going to be in the vicinity at that point. Here, that is what we will call as a small signal model. What is valid only for the neighborhoods of that. Okay. So how can you do that? You say that this particular point, let me say this capital D, let me say this capital I. That is that point. So my ID is capital ID plus one small. Okay. Then we will put a tilde. What is this? The current in the vicinity of capital I. Current in the vicinity of capital I. And that is equal to IS times exp of capital VD plus small VD tilde divided by. Right? This is what it is. There is a variance. So what I can do from this, I can separate out this. Okay? Left hand has only idea with the right hand has ES exponential of VD by VD multiplied by exp of VD tilde by. And you will be here. Okay. So now what is this first term? IS x1, IS into exponential VD by VD. Product equals to this. That is capital. This is capital. Times exponential of VD tilde. This is what? What is that? Value for that small signal. Capital I plus I. Okay. How can I approximate this fellow? How can I approximate this fellow? 1 plus. You can expand it into series, right? Yes. I will into 1 plus. We will that right. So ID is ID tilde. ID 1 plus VD. Is that right? What is ID tilde? ID times VD tilde, right? Is that? That is the small signal model of this non-linear device. It's a linear model. Okay. Whatever you say, what is that? Very good question. Question 2. How large is large signal? How small is small signal? What we have to count. We did this earlier also. Right? And somebody knows that low radius. Then we said what is low radius? Where we determine that radius is much lower than radius minus is much lower. Here he is asking, what do you mean by large signal, small signal? Or how large is large, how small is small? Okay, let's start with that. What I have done here, I have approximated an infinite series. Start with the first degree term. When is this valid? Then the second term, VD tilde by VD square by 2 is negligibly multiplied by plus. It should not have a major impact. But the second degree term, VD is tilde by VD the whole square by 2 must be much smaller than VD tilde by VD. Right? When will that happen? When VD tilde by VD is much less than 1. If this happens, that is when the signal is small. That is when the signal is small and is linear. The signal is small. So the answer of part of the question is how small is small, the signal amplitude has to be small enough that our approximation of linearization, our neglecting of the non-linear terms are valid. What is large signal? What is not small is large. If the range is higher than the second degree, third degree, right, that is one. But the other way to come at this is a large signal model because that's the complete operating range. It is equal to 1 ampere. It's maybe 1 ampere. That will be the rate. That may be the rate current of this diode. So I am considering the characteristic on the way from 0 to 1 ampere, which is a complete operating range. So large range over which is expected to operate. The model that is valid over that. But that is again only for the on state. Here, this idea is not to tell you about diode. This is to say what is large signal, small signal, how to linearize a model at a particular operating point. Anywhere else. Be able to do this, anywhere else. Okay. Now what I do is the same problem I post to the transistor. I post to the transistor. Now this is R1, R2, RC. And being a resistor, you would have solved it easily. And being a resistor, you would have solved it easily. So unfortunately, it is not a resistor. So what do you do? This is VCE. This is VCE. This is. So what I have to use? I don't know the VI relationship of the two terminals. You understand? If it is resistor, what is the relationship? V is equal to IR. If it is inductor, V is equal to LDR by dt. If it is a capacitor, I is equal to C dV by dt. Here, it is not linear. That is the problem. Okay, so how do we solve this? How do we solve this? Extending the previous one. How do we solve this? Yes, so this is why my IC versus VCE characteristic is important for me. Right? IC versus VCE. So again, the trouble is, we'll have many of them. Yeah. That depends upon what is my EVR ID. Okay. So again, sorry, I made a mistake here. Let's say this is where my base current has to flow. Right? Base current. Let's put one resistor here also. So this is my VCE. This is my IC. I both are almost equal. So what should I do in this case? What should I do in this case? You want to consider the lower RE or you don't want to consider the RE? Okay, let me not complicate the problem for you. Let me clear this. So how do we do this here? How do we do that here? I have to derive an equation for the rest of the circuit. I have one IC versus VC. Which one it will that will depend upon what is value of my IPR EV. That will say which characteristic in the family. And the rest of that I have to have as one equation. How do we do that? this. You terminate this. Come to second equal what happened here. You have some heat element. You have some R element. This is going to your transistor. This is your okay. This fellow is going to give you a VBE or IV. So you're going to know which curve you're going to be falling on that. And what is the low line? This is IC. Low line is the relationship between the terminal quantity. IC and that. So this is going to be ECC minus ECE by RC. That is the equation of the rest of the circuit. And that's the line length. That's the line. Okay, this is what is the load line. So, why I have drawn this even work that out later, it will change. This may not change, but this will change. Right? If VV changes, this will change. And if beta changes, this will change. VV and beta can also change when it makes it. Okay. So, one of these can always change. So, you normally try to make it not to change, and that is where you go into this. I leave it to you. I don't know if you have studied biasing, you should have studied. A lot of electronics education, right? In biasing, like, what you do is, now the emitter current will be fairly independent of data. Okay, that is what we get the expression for. So the expression that is there, if the RE were not there, your bias current can change. RE were there, the bias current can change. So this is all I said. So this is an example of an analog circuit. So you may say, how do we inject voltage? Where do we inject the voltage? Where do I inject my signal? Do this. This is a bias circuit. That is underlying the problem. First, what is that? You should know how to solve a circuit where you have diode or transistor element. That is where you learn to solve a characteristic. The remaining part of the circuit will be electrosphere. That is what we call a load line. The intersection of the load line and this characteristic will be the lessons here. This lesson is the basis for you to decide the bias circuit. If you know how to analyze this circuit, you will be able to design a bias circuit. These are not, I am not saying in there. You have done this and you have to do this. Right? There is a dance and other rules. So you can design this. This will make sure that this flow is always at some particular current IE or IC. It will make sure that this IE or IC will always be some 5 ampere or 20 ampere or milliampere or whatever. That is the characteristic of the circuit. So you can make it stay at a particular point. You can make it stay at a particular point. Right? Now I want to amplify. What are you going to amplify? Some voltage is there. We want to see between base and emitter. We want to create that. So how do we inject that? Let me have this line. Okay, put it there. They put it to the capacitor. DC will not flow to the capacitor. Where the signal will flow to the capacitor. This becomes an ambient. Creation of the IC circuit. This is a I can inject here. And there will be change in the IC. The IC will go to IC. This input and output capacitance will make sure that no DC flows in or outside the circuit. So the bias circuit will exist. So these are capacitively coupled ones. It is possible to have direct coupled ones, but we have to do that more carefully. Only giving you indication. This is an amplifier. This is not an example of analog amplifiers. It's still an example of analog amplifiers. Okay. So this will give your over switching, right? It is 1-0 operation. That will be known. So I can switch a transistor, no problem. Okay. Switch a transistor, I can have some. Yeah. This is here. What will happen? If I apply voltage here and the transistor comes on, this will be low. If I apply no voltage, I don't inject any current, what will happen? This transistor will be on. It's actually a mark gate. It's actually a mark gate. So there is a resistor and transistor used. Therefore, they used to call that as resistor transistor logic. Okay, they used to call it as resistor transistor logic. The trouble with this is lot of current will be flowing through this most of the time. Unless it is off. In on state, lot of current will flow. Okay. And there is not exactly plus VCC. It's not exactly. The voltage are also not there. So now what you can do is you can use this. Where can you say can proceed all movements now are secondary, right? Those things. Okay. So very good. Raise your hand. Yeah. Yeah. Is it all making sense to you? Louder. You cannot hear it. Which one is making it? Okay, you build it up. You can always. You have to ask a question. You are not even making eye contact. What's the problem? You have to learn to communicate. Nobody is forcing you. It is in your interest. Alright? Things are okay with you? Are you able to follow this? What are you understood that? Right? Yeah. You are studying this in some course now. Yes. What is it? This is confirming something that you studying as. So now tell me, this PMP is NPM. How do you connect them? This one is it an NPM? Shall I put this as a negative outside? This one. PMC. Yeah. Okay. And there are two bases. How do we deal with that? Connect them together. This is my PN. And this is my PO. Vout is connected to 0. So Vout will not be 0. Vout will be VCE sat. Okay. Point Vout. And the other way, if this yellow is open, that is connecting. That is when will that happen? This is low. That yellow will connect. Then in that case, that will become VCC minus VCE sat. Okay. So when it is VCC minus VCE sat, it is very high. You start calling this as 1. You start calling this. You start calling as 1. You start calling. So what are you saying? There is some voltage level. Not 0. Something above 0. 0.2, 0.3, something. Below that I call 0. Above something I call 0. There the idea starts. Digital circuit has transistors and they are in analog mode. Time is a continuously. Nobody can break time. The transistors inside are functioning continuously at every instant. But the circuit changes from 100 to 101, 101 to 110. This is how we are defining 1 and 0 now. So, now what is the advantage compared to this? What is the name for this? This is transistor. This is called ATM. Transistor. All these are not gates. All these are not gates. Or what are called logic inverters. These are logic inverters. So, now you are experts on that. Okay. Let us say, this is my IC versus VCE of the NPN transistor. This is the load line of the bottom. What is the load line for the top? What is the load line of? What is the load line of? So the load line has to now relate the terminal voltages are VCC minus this VCE. Okay. And where is the current? This current. There is no current flowing out to this. So here or here, doesn't matter. Okay. So what is between these two? Earlier what did we do? We did VCC minus VCE by R. When that was a resistor. Now we cannot do that. There is no resistor sitting there. Here what do we do? Conveniently I said this is VCE. Right? What will be the load line? I say VCC minus VCE by R. No, I cannot say that. VCC minus VCE is correct, but I can't do it by R. What is coming there? That is voltage across the top transistor. And if the top transistor has that voltage, it cannot have arbitrary current. It cannot have arbitrary current. That can only ask for the characteristics. Because on the basis of absorption. Those are captured with. Now what is the characteristic we are having? We are having the characteristic of PN. We are having the characteristic of PNP with the limit proportion having been taken to the top. So, if you think about it, you will see that that's a characteristic. And we something else. So the NPN characteristics or the NPN characteristics will vary. Okay, I have drawn only one NPN. You can draw family characteristics. There's a family here, there's a family there. They will go on one of these based on another one. So when this fellow is on logic low, this is not at 0, this will be at VC side. At VC side. And when the other way, this may be here. That may be there. Here you see, it is not going to 0. This context, like the MOSFET. Why? Why? What is the equivalent of a MOSFET? What is the equivalent of a MOSFET? This is NMOS, that is PMOS. Right. So now, why characteristic goes to the origin? It goes to that. Here. Here. Versus this is that. And MOS, this comes from the PMOS characteristic. When you switch, when the output is 0, it will be here. Otherwise, it will go there. And when the transistor is switching, it will start traveling on this. Over here, come back. Yes? Okay. Here. The palm is very far away. Here now, what are the changes we did now? We are having load line. When you have resistor network, you can solve easily. And one of the resistor given that transistor they have a non-linear element, you can solve it so easily. So you have to think the atoms. The rest of the circuit has to be represented. That becomes a bit terminal quantities. So the equation relating the terminal quantities of the rest of the circuit is what you call the load line. Is what you call as load line. You draw the load line and you draw a characteristic and you solve. That is the first level. Now, to make sure that your load line intersects at a particular point where the transistor is biased at a particular point. You are able to bias the transistor. What? The absence of signal input, it will stay there. Despite disturbance, it will stay there. What would be disturbance? Temperature rise. It will stay there. That's bias. Right? Once you know the bias, you should know to inject the signal and take the signal. You take the signal and take the signal out. That is not very clear. Here. Okay, why there is so much of negativeness here? Okay. So we are deriving the many characteristics, right? This is the vertical MOSFET. This is on that. If the driver, you know how to handle that. How to handle that? You have to bring in the device characteristic and the so-called load line. Next. What are you doing? The device is non-linear. So large signal model is non-linear model. So we can do a piecewise approximation. Large signal model. Some simplification. If you do some simplification, what happens? Solution is easy. Because when it is a piecewise model, why is the solution easier? Why is the solution easier in the piecewise model? Because comparing two straight lines. Comparing two straight lines. If I compare the actual characteristic of the load line, it is one exponential. That is able to solve. The piecewise approximation, yellow line is also straight line, black line is also straight line. Let us come to straight lines, even in your next standard, you will take off the scheme. Right? Yes. That is why you do a piecewise approximation to solve. Sometimes you may want to know model is operated only above an operating point. That's what happens in an amplifier. You only operate above from a point. So what will be here? That's why you go for a small signal. I'm not doing this for BJT, I'm not doing this for a MOSFET. Okay, you can do all that thing. Right? This is what we are doing. We are now slowly going into this is about the biasing. Okay. This is how you inject. That is all. Once you are injected, this thing becomes an amplifier. Okay. Now, digital. You do resistor transistor logic. Lossy. Transistor transistor logic. Less loss. As compared to BJT, MOSFET. Why MOSFET better? Uh, it can go large. Characteristic goes large. BJT, no matter what you want, push the voltage lower than DC side. Okay, you will be injecting a very high base current to make it go to that. Especially you cannot go to that. So, that is here you can do that. So this is not digital. What is the signal one? This is NMOS. This is PMOS. So, what is the name of this? This complement. If you take this is the characteristic of NMOS. What is the load line? Basically, PMOS characteristic with VDD. Okay, that is the PMOS characteristic. Where will it operate? Operate at the intersecting point. What are you doing? You are changing the signal high to low, low to high. What will happen high to low, low to high? Circles. But what is the path of movement? Will it move like this? No. There is a series of paths to the transistor circuit. At any point in this case, this will always have some potential. That determines this will always have some potential. The difference between the two is its gate potential. Similarly, this and this is the gate potential. So wherever the gate potentials are, accordingly they follow that particular characteristic. See that? They will have intersection there. Where the intersection is the operating point. There's a transient going on like that. And the end of the transient comes to the next one. So I want you to know that it makes a transient. That's why because we get into all electrons. We can do all electrons. One of the reasons we wanted a second year is we do magnetics. That more money than we started later. So now this we have studied now. Right? So now I am going to power electronics. Analog over, digital over, power. Please understand this workshop can only be indicated. Force cannot be exhausted. Force cannot be everybody can be taught. As I said, the purpose is to learn a subject, to learn how to learn. Okay, so many variants will be there. RPLC, etc. Go on for classes. You must go on for classes. And giving you those indications that against advancement, so to come to this point. Okay, now we are going out advancement, beyond advancement. So if I have a MOSFET, yes. Okay, now this is the power MOSFET. Is that power MOSFET? There is no switching in a power electronic device. Switching in a power electronic device. So what is expected? Understand? What kind of load? What is going to be applied in electric load? Going to be a software. There's going to be a load. Okay. And draw that. Tell me what I should draw. Oops. Tell me what I should draw. Draw something. And draw something like this. Okay. potentiometer at the top. So draw the load there. Okay. This is all. The loads are at reading level. What will be the direction of load current? So if it connects this will connect like this. I'm not drawing that. So when I turn this on, the field will get us connect. How will it connect? Right? After. Okay. Simplest volume switch. Now what I'm trying to say is, I want to model this for switching. Saying is it correct? Correct? Where is the diode? Between the drain and the correct. What is happening to the injector? I'm not worried about the other end of the injector. I'm not worried about that other end of the injector. But I'm worried about this end of the injector. That one will be correct only for a teaching in chopper. And this one will be correct for a wide range of circuits. So it does not matter. What matters is this current is constant. During a switching interval, this current is transmitted off. Right? Will it be instantaneous? And transmitted off no time. Everything has to take finite amount of time. What do you think is the kind of time MOSFET will take to turn on? Microseconds. 80 minutes. In fact, IGBT is simple. The model works as several hundreds of nanoseconds. MOSFETs, hundreds of nanoseconds. Maybe less than 100 nanoseconds. GaN MOSFET, closer to 10 nanoseconds. Okay, with that, sub microsecond. That's the kind of time. Within that interval, this current is constant. This current is constant. Who has to connect? MOSFET or as far as this is concerned, it doesn't mind the points connects are derivatives. So I'm writing that KCL at the node. Writing that KCL at the node. This KCL at the node is a very important thing. Without noting this, all mumbo jumbo about that, all you have to get to me. Okay. Next one. Next one. What are all the equations here? The KVL I can write. The KVL I can write. What is the KVL? What is the KVL? CVS. Then plus diode voltage, right? I will define the diode now in this direction. Okay. And you can send to that. Plus the diode is equal to this KCL and KVL come from the circuit. It does not come from MOSFET or IGBT or BJT, right? Gallium nitride MOSFET, silicon carbide MOSFET, all that doesn't matter. What is the gate resistance? Nothing matters. None of the high technologies of product matters. Basic KCL and KVL. Here, now what does it mean to solve it? That is based on characteristics. Okay? Characteristics are. How do we solve that? is this. I can say that this curve is on. Turning up. In terms of what level of the current, this current will go to 0. That current will become 0. Over a period of time. Over a period of time. What will happen to the voltage? This curve will be 0. Gradually it will go to 0. Over a period of time. This is what you want to understand. This is what you want to understand. How this happens. Right? As I asked in the morning, how do we approach the problem? How do we? First, to understand the circuit. Respect the SLK. That way I do that. If the distribution in a hurry, look at what MOSFET is. Oh, I will. Now, what have you got to do next? What is relevant now? If you look at it from the overall perspective, what will be the load line? What will be the load line? VDC minus that. What will be the load line? Mostly, the voltage at this point will be either VDC or 0. This voltage will be either VDC or 0. This is always VDC. What is the current to that? What is the current to that? Don't worry. Answer. Okay. What do you do here? Does the characteristic of matter? Yes. Yes. Why does it matter? If it has certain VGS at a particular instant of time, and it will have some high transistor, which is actually ID. No, actually, ID is the master terminology. It has certain VDS. It has certain VDS. These three have to be related. These three have to be related. VGS, VDS, ID. They cannot be related. Why? It's a MOSFET. This is the physics of the MOSFET. So who gives you this relationship? Characteristics. The characteristics gives this relationship. So let me write down the characteristics. Okay. This is ID. This. I will not enforcing a discipline. A discipline should be that and attack parabolic curve. The parabolic curve. On the right hand side of the parabolic curve will be flat. Below that it will be inverted parabolic. Okay, me. You can follow yourself. Okay. Right. Now, let us say the device is off. The device is off. So what happening? I is 0. And this side is okay. I think I should not confuse this side because how this is transferred. And still is there. So where is the operating point here? When this is off. At VDS. Current is 0. This is VDS. That is operating. Okay? The MOSFET is on. The load line is going to that. Right? Later what left? Later what left? Later what left? The MOSFET is no longer left. Based on VGS. So let us say this is the VGS they are operating. This is VGS is plus 0. This is where they are operating. Where will it come? It will come to a particular point here. Here, and it is equal to the. Okay. This is MOSFET. This is here. comes, how do you move? Next point is, how do you movement has to respect the characteristics of MOSFET, has to respect. Okay. But what does happen now? You started telling me, I'm not doing the gate side characteristics now. Okay, we're turning on. What? Turning on. So the gate source voltage is gradually increasing. Gate source voltage is gradually increasing. As long as until it increases to be threshold, what happens? This curve will stay here. This curve will stay here. That is, if your VGS higher than the threshold, it's level. If VGS becomes greater than the threshold, what happens? Current will start building. So the current will start building means it is moving up, vertically up. So what happens to the voltage? What happens to the voltage? No. Current starts building. Give some number for the current. Let's say another ampere. The current is rising from 0 to 1 ampere. What happens in 99 amperes of current? Going to the diode. 99 amperes of diode current is flowing to 99 amperes flowing to that. What is the potential here? The potential is still increasing. Potential is still. I didn't want you to make this. That's why I can now say. But this, I was still connecting. I was connecting. I was about 0. So, now 1 ampere becomes 2 ampere. 2 ampere becomes 3. 3 becomes 5. 5 becomes 10. What happens? What happens? This moves here. Until when? Until when? Until maybe. So that is when it has become higher, what happens? Diode is really diode is really diode does not have to carry the current. The entire current is moving through. Now the diode can start moving up. Keep counting as in a bed, not a instant counting as in a class, right? Class you are counting. Right? Yeah. So now the diode is off. When the diode is off, it is blocking some potential. You can see, let's say, it's 300 volts. 300 volts can become 290, 270. Right? Diode will take 10 volt, 20 volt, 30 volt. Then what happens to VDS? 290, 280, 270. So, first it moves in this direction. Now, okay, until eventually the story continues. When it is moving, the current is constant. Main current is constant. And the main current is proportional to VGS minus VT. Therefore, VGS minus VT is held to be constant. The circuit will force VGS minus VT to be constant. That means VGS will be constant. During this interval, you will find the gate source voltage is constant. Okay, this will continue till when? What happens after this line? The physics of the MOSFET changes. The physics of the MOSFET changes. The MOSFET goes into so-called saturation region to so-called saturation. Okay, the saturation region is only proportional to VDS minus V to the whole square. The diode region, ID is K1 VDS, K2 VDS square. V1 and 1. Okay. when it comes here, what will happen? The gate voltage will increase, right? When it moves from here to here, when it moves here, it's causing different lights. Causing different lights. Finally, this will come here. So, when it causes different lights, what is happening? It is this. Finally, we reach the destination. That's where we reach this. That's where we reach this. Here. Isha. Yes. So it's impossible now for you to see what happens to the voltage and all the level. No, and information. And you draw how the rate, how the delays are in the voltage. Let's say clearly, voltage. Initially, delays voltage was the VDC. Yes, VDC. Current was 0. Then what happens? Current starts. Current goes to feedback. Okay. Take that as a straight line. But again, depends on some physics. But let's take it as a straight line. Current which is something like this. After that, what happens? Voltage starts falling. Until the voltage is really easy. Until the voltage starts falling. Okay. There again, there is a lot of delays dependence. Cost on alternative varieties. Okay, how will it look like? How will it look like? Current is 0, current goes to I. Current goes to what happened to VDC? VDC. This is first picture. So what's happening here? What's happening here? Large voltage and large current are there simultaneously. Okay. What is power dissipation? That will device. Don't get no current is going. Current is going. You can bring source voltage. How much the power dissipation? How is the power dissipation? How much is peak power? VDC multiplied by how much is time? That is what you call as your roughly that's called P on per now. Roughly that's called P on per now. So what is done is typically this time when it rises, that is called T rise. This is called T rise for the current loop. And this particular level is called T rise of the current. It's called T power voltage. Let us give some simple names. There are no complications. No calculations. So this is the rise time of the current. So the area of the triangle gives you the area gives you so much energy is lost. So much energy is lost. Okay. So if you take a train, the next train has 7 megawatt of power is required. That's the train. 3 times 6 minutes. let's take this one conductor that has a DC input that 15 amperes. That is an annual 100 amperes. What is the product? 1.5 megawatt. Product this 1.5 megawatt. What is observed in that? Those in the IGBTs, several hundreds of nanoseconds, like easily 1 microsecond. If you take the 1 microsecond, 1.5 megawatt. What is the area? Half. 1.5 into half, 0.75. 0.75 joule. This is microsecond. So 0.75 joule is lost in 1 minute. Okay. Now you have to say what happens to the gate. What happens to the gate? What happened at this point when current started rising? That is where gate crosses the threshold. That is where gate crosses the threshold. So let me put the gate source over the gate. So what happens in the gate is kind of RG. Okay. And we have a MOSFET like this. This is your gate, this is your source. So the pulse is applied here. The pulse is applied here. Pulse is applied. So this pulse is applied here. That is going to rise. So when it rises like that, the pulse rises. Pulse will rise like this. The voltage would have actually been negative also. The gate voltage can be negative also. In response to that, this current will start increasing. This should have happened earlier, sir. This will happen earlier. And this is your VGS. That is your V threshold. Good. When it reaches V threshold, conduction begins. When there, conduction begins. Later, what happens? Continues for a long period of time. For a long period of time, the voltage remains steady. When it moves here, what happens? The voltage remains steady. Right? So, the gate source voltage remains steady for quite a while. And after that, sorry. This gate source voltage will continue to rise until when? After this point. That means current is reaching full value. Very good. So the current is reaching full value at this instant. So the gate source voltage will continue to rise to full value. Okay. So at this particular point, so this, this particular point, where it's okay. So like right here, that is R here. So the gate will start from here. Start from here. This V threshold is 1, 2.5. I will start rising here. And continue here. This voltage is called V Miller. This voltage is called V Miller. That is constant. At this point, the voltage will continue to be here. This is the gate source voltage. This is that gate source voltage. And this is there is still in that saturation period. Finally, when it goes to the triode region, go like this. So here, finally, this might start from, let us say, -1. Okay, the gate source now. There's no jump. Gradual rise. When it goes to this. So up to this point, rate source is constant. That is the Miller region. Up to this point. Okay, something happened with line by base. Okay, this is the Miller region. This is where Miller region. When this region, the gas is constant. When it goes inside, the gate voltage goes on increasing. Finally, so the Miller gate voltage is that gate voltage at which the saturation drain current is equal to the load current. Okay. The device will not operate in the saturation region. The device will operate in that linear region, not even with that diode. The diode also goes up to the origin. There is a state. Everything is a parabola. It will not operate in the actual parabolic region. Parabolic region also goes up to the origin where the parabola looks like a straight line. That is where it will operate. Okay. So when it turns off, what happens? When it turns off, what happens? When it turns off, what happens? Then we become a color. What color? So we used to play again, color, what color, do you choose? Right, so green. Right? There is a start. That is where it is on. On is the gate voltage now 15 volt. Gate voltage is now 15 volt. Gate circuit is given a negative pulse. So the gate voltage starts reducing. But when the gate voltage starts reducing, the drain current cannot change. Why? The drain current is equal to load current. The drain current is equal to that load current. So this valve will move in this direction. This will move. As it moves in the direction, it is going to the lower and lower current. Which means the gate source is reduced. Which means that gate source is reduced. Okay. And once it reaches this point, that is the Miller rotation. That is that Miller rotation. And from here, the gate source voltage will continue to be a constant. But along here, the voltage goes on increasing. The voltage goes on increasing. Now, this voltage is entirely VDC. When this voltage is entirely VDC, the diode does not have a clock. When does the diode clock? Only when it is off. Okay, when it is off, it will block. Only one block. Now the diode doesn't block. The diode is getting power best. The diode starts. When the diode starts connecting, the transistor current reduces. Here, I've compared to my system of where. Now you need to look at that. I'm not going out anywhere. Right? My email address is known. Someone knows me. Right? I give you. Right? You may have a remote meeting. Understand? But I want you to know on Saturday. This is basically the case. This is the way it is. I think the next is very clear about this. Right? Okay. That's as far as you are clear about this. As we go. Right. Okay. So I will read based on what he asked me and what I know. There's a thing called desaturation. That's what is. So let's see this one. Yeah. Yeah. So, there's a fault. What happens to the fault is more current flows to that. Let us say 15 volt is there in the gate source. You have tied it to 15 volt supply now. So you are following a particular characteristic. The device is conducting, let us say, 50 amperes of current. Due to a fault, 50 ampere becomes 100 amperes. What happens? ID goes up. When ID goes up, what happens? VDS also goes up. Okay. So the increased VDS is a sign of increased ID. So this is sometimes you call as it coming out of saturation. Like in the if you look at the BJT terminology, it is coming out of the saturation. It is coming into the active zone. It is no longer in the linear zone. It has gone into the triode, non-linear portion, right? Even further. So you sense that voltage. And if that voltage is higher than some level, you know there's a fault. You turn off the gate pulse and protect the device. Okay? Clear? All right, thank you. So we'll come back and we'll look at some power converters. What, Sriraj? Lot of trouble. Huh? So let's look at electronic switches, right? We have been with IV and all that for a long time. Finally, now we are getting closer to switching action. So let's recall the many characteristics that we did. Let's say there is diode. So how is the characteristic looking like this? This one. And this side, so long this thing, and there's a breakdown. This is how the diode's characteristic is going to look like. So what effectively this means is, when the diode is on, there is some small power drop. There is some small power drop. If I ignore the power drop, this is my ideal on characteristics of the diode. And I ignore any leakage, this is my ideal off characteristic of a diode. So I can write that as ideal on, and this is my ideal off. So I look at diode as a switch which can conduct current in only one direction, which can block voltage of only one polarity, Next, let me come down to the BJT. And when it is off, when it is on, it is somewhere here. So when it is off, this characteristic is here. Maybe I should make that now black because it's become red. So this is my, I don't know why I'm messing up with the colors now. Okay. Oh. Right. Okay. This is my BJT characteristic. This is my CMOS characteristic, or sorry, NMOS. So when it will be, when it is on and off, what happens? When it is on, this fellow is likely to be somewhere in this region. When it is off, this will be here. That is your off characteristic. So if I ignore this drop, this is my ideal on. This is my ideal on characteristic. And this is my ideal off characteristic. So BJT is a switch that can conduct current in one direction, that can block a voltage in this direction. So you can see this is positive and this is negative. As a result of this, if I connect a BJT and a diode like this, what will I get? This BJT will conduct in this direction. This diode will conduct in the opposite direction. And which direction it will block a potential? This is the only direction where they will block a potential. Okay, so that is a diode is a single quadrant switch. BJT is also a single quadrant switch. I can come up with a composite switch. Okay, and this is in parallel, and it's a parallel and it conducts in the opposite direction. Therefore, there is a slightly funny term called anti-parallel. So you have that anti-parallel connection. So this is so you call the switch as a single quadrant switch. Single quadrant. Only positive current and negative voltage. This is also single quadrant. It's positive current and positive voltage. You are reverse connecting it. Therefore, you are having positive and negative currents here and voltage here. You are able to realize this. And when you do a MOSFET, what is going to happen? When the MOSFET is there, you are going to be here. This is the MOSFET's off characteristic. And when it is on, this is your forward drop. This is your forward drop. If you ignore this, this is your ideal on. Clear? Yes? So I can look at them as switches and they operate in multiple quadrants. The point that we have to recognize is when you say switch, how many states does a switch have? 2. Either it is on or it is off. What happens when it is on? Conducts a current. That can be taking the terminals as A and B, can be from A to B, or B to A, or both. Every switch cannot do everything. Some switch will conduct only from A to B, some switch will conduct only from B to A. For example, a diode will conduct from A to B, this will be from B to A. And if you put the two in anti-parallel, both can connect together. And similarly, when it is off, it does not conduct current. But when it does not conduct current, what does it do? It blocks a voltage. That voltage can be one polarity, A positive with respect to B. Or sometimes it can be B positive with respect to A. Or sometimes either way. Okay. So we are now looking at these examples. In this is a MOSFET. And MOSFET, as we already have seen, you already have a anti-parallel body diode. So this fellow conducts in one direction. Actually, the channel can conduct in both the directions, but predominantly, let's say this and this. Okay, this is capable of conducting in both the directions. Actually, the diode can conduct in only one. The channel can actually arguably conduct in both the directions. Okay, but let's not get into that. So it can conduct in both. It will block a voltage of this polarity. It is block a voltage of this polarity. So in this sense, this is itself is a 2-quadrant switch. Is a 2-quadrant switch. All right. So what else you can look at? You know thyristor. You know thyristor. So A and K. Can thyristor conduct in both directions? No. What is the direction it can conduct? Only one. How can it block voltage of both polarity? Yes. If it is reverse biased, it will not conduct. If it is forward biased also, if you don't release the gate pulse, if you ensure that it does not turn on, it can block. So this is also a 2-quadrant switch. This is also 2-quadrant switch. This 2-quadrant switches are these 2-quadrant switches are bidirectional conduction and unipolar voltage. So the conduction in 2 directions, whereas this switch is bipolar voltage. This is unidirectional current. Unidirectional current, but bipolar voltage. Okay. So can I use two devices as a composite switch to realize this? I can. What is this? BJT with respect to the BJT is gated high, the switch is on. The BJT is no base, then low. It can conduct in only one direction. Okay. The diode will block any voltage of this potential. The BJT will block any voltage of this potential. So a BJT and these are similar. They are functionally similar. But mostly in the modern context, you have switches that are conducting in bidirectional case. Okay. All right. That's also related to what we look at, current source inverter, voltage source inverter, and all that. So now, can I look at 4 quadrant? Can I look at 4 quadrant? Sometimes the switch will have to conduct in both directions, depending on the external circuit when it is on. That is what these AC switches do. In the AC switch, what does it do? In the positive half cycle of current flows in one direction. Negative half cycle, current flows in the other direction. And when the switch is off, in one half cycle, it blocks a positive voltage, in another half cycle, it blocks negative voltage. So there can be 4 quadrant switches. So how can I realize a 4 quadrant switch? One way is, I take the same fellow, I put the inverted one. I'll put this fellow can conduct like this. I'll put the other fellow in the other direction. This is one example of a 4 quadrant switch. A simpler example of a 4 quadrant switch is, you already have a MOSFET with an anti-parallel diode. Already there are 2. This is a 2 quadrant switch. Block only one polarity, conduct in both directions. I can put another fellow here. So this is one MOSFET and the other MOSFET flipped around. They are flipped around and they are connected in series. Okay. So you can use 2 single quadrant switches to realize a 2 quadrant switch. By anti-parallel connection, you can go make that into bidirectional conduction. And this is in series. Okay. So I use this funny term called anti-series, because they are using anti-parallel. Okay. Basically means there's no such thing as anti-series. That way there is no such thing as anti-parallel also. There's only parallel. Okay. What do you mean by series and parallel? Common. Voltages are same parallel. So when do you say 2 elements are in series and 2 elements are in parallel? Basically, it is more than it is more to do with the path than with electric current and voltage. So 2 elements are in series. If the path involves crossing A, it also involves crossing B. If I'm going through A, I have to go through B also. Then they are in series. If I go through A, I cannot go through B. That's parallel. Okay. So, R and N. Yes. So this is a 4 quadrant switch. That is also a 4 quadrant switch. Okay. Now, any question I can answer. But you will know more of this. This is only to put things in place. I have a lecture called electronic switches in the NPTEL there is an NPTEL course on PWM. Okay. So more detailed one, you can certainly find that here. Okay. So in case you're interested or you want that, you can try that. This is dealt with in some level of detail there. So why do we need all that? Actually, we need this in a power converter. That is why we did all this now. So now let us start with why do you need a power conversion. Some example that we'll have is, let us say I have a higher voltage. I have 100 volts. And I have a load that needs only 50 volts. Okay, how do I do that? Somebody is trying to reach me. Sorry. Just a minute. Should I turn this off? How do we do that? The question is, how do we do that? Right? Everyone knows that if this is a resistor, I can also do with a, if this were a resistor, I can always do this with the resistor. If the load is a resistor, right? I will need some V naught. This is my RL. So I can vary this resistance. But that will apply only when the load is resistive. And not only that, there's going to be always a dissipation in the series regulating resistor. These kind of things are all done conceptually by the voltage regulators. Where the voltage regulators do this. You might have seen an IC called 7805, no? Have you seen an IC called 7805? Many voltage regulators are there. This fellow will give a 5 volt output. This fellow will give a plus 5 volt output. This will have a V in. So the V in may be in the range of some 7 volt to 15 volt or whatever. Some permissible range is there. And this is your common output. Maybe they'll have some capacitance like this. This is a regulator. This has many transistors internally acting in the active mode. So the transistor will be dropping. Let us say if this is 10 volt, the transistor will be dropping the difference between 10 volts and 5 volts. The transistor will be dropping 5 volts. So what does it mean? The entire load current will flow through the transistor, 5 volt. So 5 volt into the current is going to be a loss. So these are linear regulators. What is linear about them? The transistor works in the linear mode, not in the switching mode. Linear basically means active mode. That is why they are called linear regulators. That's why they are called linear regulators. Otherwise, the characteristic is not linear. What is the characteristic of a regulator? VO versus Vin. Regulator means voltage must be constant. That is a regulator. And it will work only above certain input voltage. Above that, it has to maintain constant. This is a regulator. It's not a straight line or something like that. Okay. What is linear is something is working like that. So it is better to go for switching. It is better to go for switching. What is the advantage of switching? Switch is either on or off. The switch is only either on or off. What happens when it is on? Drop is 0. The voltage drop is 0. What happens when it is off? Current is 0. So when drop is 0, power is drop into current. In place, power is 0. Here also, power is 0. If you use a switch, whether you can successfully accomplish the task or not is another question. But if you use a switch, the switch is only either on or off. And ideally, the switch drops no voltage. So the power dissipation is 0 volt into current. So 0. And when it is off, it blocks some voltage. V blocking, but 0 current. So V blocking into 0 is 0 watt. So neither in the on state nor in the off state, it will dissipate any power. So ideally, it can give you 100%. You can see the resistance network ideally also can't give you 100%. Okay, even theoretically that's not possible. Here it can give you. Okay, so then the question is, how do I do this with a switching network? Question is, I want to do this. What should be in the box? What should be in the box? Okay, now we'll go into that. What should be there in the box? What devices are permitted in the box? The box will have switch. Then what all the box can have? The diode is also I'm counting as a switch now. The box can have inductor and the box can have capacitor, because all these elements have no loss ideally. Okay, from that perspective, I'm allowing myself switches, inductors and capacitors. Okay, now let's break that. What do I do? With 100 volt, I need 50 volt. What do I do? I have a load. I connect it to 100 volt. Then I short the load. When I short the load, what is the voltage across the load? 0. When I connect it, it is 100. That is possible through switching action. So let me put that. When I have 100 volt, I can connect 100 volt across my load. And I can also apply 0 across the load. I can once again make it 100 and once again I can make it 0. If I do this, in some sense, what I'm applying is an average voltage of this. And this average voltage is duty ratio times. Okay, this is one idea. If I can do this. So to do this, what kind of switch is required? Okay, this has to be realized. So this is my 100 volt. So 100 volt should come or 0 volt should come. Means I should have a switch. If I connect this here, 100 volt. If I connect this here, 0 volt. So it is possible to do that. This will have a voltage like this. So what does this achieve? Pulsed voltage. The average voltage is reduced to 50, 60, 70 or anything you want. But still, it is not an instantaneous voltage. Okay. So I have a load. The load could be whatever it is. If the load is resistance, what will happen if I connect this? The load is resistance. What will happen if I connect this? The current will go up and down like this. The current will go up and down like this. This is when resistive load. Huh? Correct. The current will be this is if it is an RL load. If it is an if it is a resistive load, the current will also be pulse like that. This is not certainly a DC voltage. Okay. If it is capacitive, or if this is a voltage source, what will happen? You just can't connect. You just can't connect. Because there are elements like capacitor. And there is an element like, let's say, battery. You cannot apply a switching voltage there. If it's a capacitor, you are forcing dV by dt to be very high. dV by dt is almost infinity. That means you are forcing infinite current through the capacitor. Not only capacitor, anything that has a tendency to resist change in the voltage. Anything that has a tendency, so it can be a voltage source or it can be a capacitor. These kind of things cannot be connected. Whereas if it is an RL load, it is better. So what the load wants is only DC. What is the difference? The difference. So there is a pulsating voltage, sudden change in voltage. Who can absorb sudden change in voltage? Only an inductor. Only an inductor. Only an inductor can absorb sudden change in voltage. Normally you would have heard inductors for smoothing current. I say this for sudden change in voltage. So I have pulsed voltage on this side. I want DC voltage on the other side. What element can come in the place of the inductor? Tell me that. What element can come here? What element can come here? If I connect a resistor there, what will happen? Only jump up and down. If I connect a capacitor there, voltage cannot increase in a capacitor. So what is primary? What is primary? Primarily, the voltage difference somebody has to handle. And the only person who can handle the voltage difference is actually an inductor. Actually an inductor. You want a significant voltage to be dropped and dropped at high frequency. That means you want someone who has a high impedance at high frequency. Who has high impedance at high frequency? Inductor, omega L. Okay. What is the effect of switching voltage on an inductor current? If the inductor current rises like that, if the voltage switches, nothing. Only the direction will change. So only the inductor can change a sudden changing voltage across itself. So when I do that, this current will become like this. My current will become, from here it will become like that. That is better. Why? Some ripple is there. There is some Ripple. So what is flowing through the inductor? There's a DC plus some ripple. I want the DC to flow here. I don't want the ripple to flow through the load. So what do I do? Put a capacitor. Capacitor will not take DC, no matter what. Tiger can eat grass, but capacitor won't take this. Okay, only when there's charging or discharging, there's going to be, not otherwise. So, if I put something parallel, the DC component will flow only through the load. It will not flow through the capacitance. What will happen to the AC components? Capacitance impedance is 1 upon omega C. Higher the omega, smaller the 1 upon omega C. So it offers very low impedance to higher frequencies. So it says Aja Bhai. And all the higher frequency components are going through. Okay. So you have solved the problem. The role of the switch is reduce the average voltage. That is what did the voltage reduction for you. 100 volt has become 50 volt, 60 volt, 70 volt average because of this. What did the LC do? Smoothen the gap between the ideal waveform and the actual waveform. Smoothen the gap between ideal waveform and the actual waveform. Okay, and you look at it, it is a single pole double throw switch. What is connected across the throws? 100, 0. Voltage source. Voltage source is voltage stiff. It should not be shorted. And it will not get shorted because it is across throw 1 and throw 2, they will never get shorted. What is connected in series with the pole? Inductance. Inductance is current stiff. And something that is current stiff should not be opened out. And if it is in series with the pole, it will not get opened out. Why? It will provide a path either through throw 1 or throw 2. But it will provide a continued path for current to flow. In many power electronic converters, you will have a single pole double throw switch. You will have a single pole double throw switch. And voltage stiff elements like capacitors and voltage sources will be connected across the throws. And current stiff elements like inductors, current sources will be connected in series with the pole. Okay, that's a lesson from here. So this is now what is called as a buck converter. So what is a boost converter? I have the inverse problem. I have 50 volt and I have to make it 100 volt. How can I do that? How can I do that? $100 volt to 50 volt is easy. Why? I will connect this 100 volt for 50% of the time, 0 for 50% of the time. 100 volt for 50% of time, 0 for 50% of time. On an average, I can get 50. You want 60, I can connect 100 for 60% of time, 0 for 60%. 40. 60, 40, 60, 40. So, reducing is easy. How can I increase? How can I increase? Store somewhere and add. Where do you store and add? What do you store and add? You have to store voltage. You will store energy. Energy you are storing everywhere, no? Correct. You are storing energy here also. Inductor storing energy wherever it is. So how do you do that? There are quite a few ways to recognize this. Okay. Now, let me redraw my buck and try to understand what it does. Oops. No. Wow, now I can do this. Yeah. That is learning training workshop. Huh? Okay. So I was teaching in the 19th century. NIT Goa has brought me to 21st century. Okay. This is now, let us say 100 volt. This is 50 volt. This side is a source and this side is a load. That is why you are calling it as a buck converter. That's why you are calling it as a buck converter. Now what I want to do is, I want to make this side a source. I somehow will make this side a source and I'll somehow make this side as load. And that is still 50 volt. This is still 100 volt. So the power, I should make it flow in the opposite direction now. And I should make power flow in the opposite direction now. The question is, how do I do that? The question is, how do I do that? Okay, we can go on. Are there any thoughts that you have? What is there across the load now? Capacitance. And the property is voltage stiffness. The load is presently voltage stiff. The load is presently voltage stiff. So if I have to achieve that, I should make the source voltage stiff, not a problem. I should make the source voltage stiff, not a problem. If I replace this by this, that is also voltage stiff. This is also voltage stiff. And this is the load. Load should become voltage stiff. How can the load become voltage stiff? Now what should I do? Now what should I do? Which side voltage is high, which side is voltage is low? Source side is high, load side is low. Source side is low, load side is high. So what is the switch I should connect now? Okay. Let me put the numbers here. 100. Okay. What is the voltage here? 0. What is the voltage here? 50. So the pole voltage can sometimes be equal to throw 1 voltage, sometimes to throw 2 voltage. And its average value is in between the two. The average value is in between the two. Okay. Yes. Pole voltage. What do you mean by pole? This is what I call as pole. This is throw 1. This is throw 2. So the pole voltage can sometimes be 100, sometimes be 0. So on an average, it has to be between 100 and 0. Okay. So this is the lowest voltage. This is the next voltage, that is the highest voltage. So what does it mean? One of the throws will have the highest voltage. One of the throws will have the lowest voltage. And the pole will have a voltage between the two. What are the three voltages here? 0, 100, 500. So the throws should get 0 and 100. The throws should get 0 and 100. Where is 100? This is 100. This is 100. This is 0. Let us not be in a hurry. So the throws and the pole. Where is the pole? Pole is somewhere at the middle. Then am I doing something correct now? So this is 0, this is likely to be 50. But the trouble is, this is not always 50. Its average is 50. This is hitting 100, hitting 0. Dhum, 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 dhum. The average is 50. So this cannot be connected to a capacitive source or a voltage stiff one. So what do we do? This is a boost converter. This is one way of approaching boost converter from a buck converter. There are many other ways. There are many other ways. To get a sense, I should look at Sriraj's face. Okay, this is a now boost converter. What is remaining? These are single pole double throw switches. I have to replace them with transistors, diodes. Now, the current in this is going to be like this, because that is how the power has to flow. Because you want the power to flow like that, load current is like this, so you want power to flow like that. So that is how it must be. So this pole will conduct in this direction. Let me just change the color there. This fellow will conduct in this direction. When this is connected there, it will conduct in that direction. It will conduct in that direction. And this fellow will block something like plus minus 50 volt, and this fellow will block something like plus and minus. Okay, that is the voltage polarity, and that is the current polarity I want. So what will I get between P and T1? It will conduct in this direction. It will conduct in this direction. It can block a voltage of this polarity. So that is between my pole and this throw. What is between this and that? It can conduct in this direction. It can block this polarity. Okay. This exercise you can do for buck also. There are several ways by which you can do this. Okay. Something that is very standard that Professor Ramanarayanan used to recommend. If you look at that NPTEL PWM lecture, okay, I think there is one lecture number 2 or something called DC-DC converter. So if you see that, there will be one particular approach. But there are many more. So this in the class, depending on how the students are, this even goes on for a long time. Students will get curious and say, why don't we do this? Why don't we do that? Okay. So you can also think about that. If necessary, we can also think of 1 or 2 more ways of how you can approach this. The point is, as I said first long back, right? In BJT, we said this, for example. I don't want to start saying this is a BJT. This is a BJT. And now, under this condition, this is what it does. It is all right. But the entire approach starts from what is BJT given to you as a black box. BJT has somehow come into the world by the time you are understanding that. So that doesn't give you much insight. Whereas the people who invented the BJT, I'm not saying you reinvent, you cannot do it now. It has already been invented. They would have gone through a lot of intellectual process, a lot of struggle to understand that. You must get some feel of that. Then you will not have a problem like recalling the structure of MOSFET. You understand? Because your starting point is an image file and the file gets corrupt. You can't reproduce. If you are going to reproduce image file, Google is million times better than you. Forget AI tools. Google can give you so many images of so many things. So your thing is not in finding the image. Your thing is to know if there's a converter. It is not to draw the converter circuit. You should know how the converter circuit came up. You have to go to a more fundamental level and start from that. That is why I didn't want to tell you what is a boost converter. So I told you something about buck, and that too we didn't draw a buck directly. We had some reasoning. we wanted to reduce 100 to 50, and what is all permissible, switches are permissible, LNC are permissible, because none of them is lossy. And then how do we do that? We can use a single pole double throw switch to reduce the average voltage, but now pulsed voltage is there, and what you want is a constant voltage. How do you absorb that? The difference between the two can be absorbed only by an inductor. Among whatever we know, an inductor is mandatory, and that inductor comes in series with a pole. And pole is what provides a continuous path for current flow. Throws provide a discontinuous path. And the voltage stiff elements should never get shorted. So they will get connected across throws. The current stiff elements should not be opened. So they will come in series with pole. So power electronics is better understood in terms of the switches, current stiff elements and voltage stiff elements, rather than confusing about converter, inverter, is it converter or inverter, and going all that kind of arguments and things like that. Okay, this is now very, very neat and clean way. Is it AC DC or DC AC? Power can flow in both directions. Okay, I had very difficult questions. BLDC motor, PMSM, is it a DC motor or AC motor? Huh? There is some law clause somewhere in some import law something which says for one you have to pay less customs duty, other as other custom duty. So the company insists one that is a lower custom duty, the customs officer says the other, or he wants us to say whether that is correct. So the idea of whether BLDC and PMSM is DC motor or AC motor, how do you respond? The question of whether it is DC motor or AC motor came at a time when motors ran purely on DC or AC. When you had DC motor and you had induction motor, synchronous motor, DC motor was DC motor. Induction and synchronous motors were AC motor. Now all the motors are power electronically driven. The output of the inverter is AC, but the input to the inverter is DC. I can even argue that an induction motor is a DC motor. If I give a lawyer some money, he can do better arguments. Finally, electrical engineers will start believing that an induction motor is a DC motor, because DC is what is used in doing that now. BLDC and PMSM are all motors that cannot run without power electronic control. The difference between conventional machines and the novel machines, which we'll do tomorrow, the conventional machines can run on DC or AC supply. They may run better with power electronic controller, but so-called non-conventional machines or special machines require a power electronic converter to feed. Brushless DC, PMSM, switch reluctance machine, all these certainly require a power electronic converter. Without that, you cannot be running them. Okay, so that is one essential difference coming up there. So now this gears up that we have to find out what is the next level of doing that now. So I want you to think now. So I just buck and boost, everybody knows, and this is for unidirectional power flow. It is only, that is why I said source and load. But there can be bidirectional DC-DC. You're having battery. Sometimes you want to charge the battery. Sometimes the same battery gets discharged and supplies power. So the converter can be a bidirectional converter. So I want you to look at how that is a bidirectional converter looks like. Now, I didn't do this part here. Is this correct? No. What am I doing? Yes. What kind of converter is this? What kind of converter is this? Huh? Buck. Why is this buck? Whatever is VDC, this is pole. The average voltage here will be lower than that. The average voltage will be lower than that. And the average drop across an inductor is 0. The average drop across an inductor is on a side. So the entire VP average will come here. And the VP average is lower than VDC. So it is certainly a buck converter. So let us put the switches here. How do you put the switches there? when this is conducting, the current will be in this direction because that is the direction of your load current. The inductor current is in this direction. So when it is freewheeling, this current will flow like this. And in the active state, this current will flow like this. And when this fellow is conducting, this fellow will block a voltage, positive and negative. And when this fellow is conducting, this fellow will block a voltage that is positive and negative. As a result, I will have to conduct a device like this. This is how I realize a buck. Can I make it bidirectional? Okay, can I make it? Even before making it bidirectional, there are reasons why sometimes you can use a MOSFET, but I'll include the bidirectional portion now. How can I make it bidirectional? Bidirectional means what? When current flows like this will flow, this will flow. That will be the direction of current path. On the other hand, sometimes power will flow in this direction. The average current will be in this direction. Now, this fellow has to conduct like this fellow will conduct like this. If I have to do that, what should I do? I put a anti-parallel diode, and I put one this becomes bidirectional. This becomes bidirectional. So when it is bidirectional, normally this portion will not be loaded with a capacitive filter, but it will be some voltage shift element. For example, let's say that can be a battery. This can be a battery. Okay, so we have very easily made that into a bidirectional one. And you know some switch is naturally bidirectional. Huh? Yes, DC motor can do. You can also put a DC motor here. If you put a DC motor here, the motor has separate field winding. What will happen here? Sometimes the motor power will flow in this direction, sometimes it can flow. What does that mean? This is motoring. This is regeneration. This is regeneration. So the previous one would have been called a 1-quadrant chopper. This is now called a 2-quadrant chopper. This is now called a 2-quadrant chopper. And in this polarity doesn't change. This polarity doesn't change. So for a DC motor, when the armature voltage polarity doesn't change, that means the back EMF polarity doesn't change. Back EMF polarity does not change basically means it is spinning in the same speed, the same direction, positive or negative, whatever, only one. But the current can reverse. How can the current reverse in a DC motor machine? When the armature voltage is greater than back EMF, current will flow in one direction. When back EMF is greater than armature voltage, it will flow in the opposite direction. And armature voltage is at your control. Back EMF is whatever, depending on the speed and the flux. So let us say the motor is operating at 180 volts, back EMF. It is motoring because you have applied 190. You reduce 190 to 170, the motor will become a generator. Can you reduce 190 to 170? Yes, you can do it with a power converter. You can do it with a power converter. In that case, what will happen? Power starts flowing in the opposite direction. The motor is regenerating. So the stored energy can come down. The motor can decelerate faster or come to stop. When it comes to stop, you call it braking. And this is regenerative braking. Otherwise, it's deceleration. It is a regenerative deceleration. When it is regenerating, it will pump in the other direction. Again, it can start motoring back. This is what you can call as a 2-quadrant chopper. So since professor said about that, can I have 4-quadrant chopper also? Can I have 4-quadrant chopper also? Yes. So what is that I have done here? I have Where is my DC motor connected here? Now here. This is how my DC motor is connected. What I will do is, I'll remove this. I'll remove this fellow. I'll remove this fellow. I will connect DC motor here. I'll have one more leg like that. Sorry. So this is VA at point A. This is VB. So what can be VA? VA is going to be duty ratio of A into VDC. Duty ratio of A into VDC. It can be 0 to 1. So it can be anything but that. What is VB? Duty ratio of B into VDC. It can also be between 0 and 1. If dA is greater than dB, the polarity will be like this. If dB is greater than dA, the polarity will be like this. So now what happens? The armature voltage polarity is also changing. Not only the current direction. And this is a 4-quadrant chopper. This is a 4-quadrant chopper. Okay. And in that 4-quadrant chopper, the same 4-quadrant chopper, okay. I'm removing the DC motor. I'm putting a load, AC load. This becomes a single phase inverter. This becomes a single phase inverter. The only issue is this dA will not be constant. This dA and dB will not be constant. They will not be constant. They will be modulating. This may be some 0.5 plus some capital D sin omega t, because D can be only between 0 and 1. The average is 0.5. This can be 0.5 plus D sin omega t, and this can be 0.5 minus D sin omega t. If we simply modulate it like this, it's an inverter. The power electronics is so simple. Power electronics is so simple. You have not studied power electronics, no? Next year you can give exam directly. You are the only second years now. 3 of you only left. So you are the battle-hardy people. Others have left off. Wow. Good. I haven't seen many of them. Very good. Was this understandable? You're able to follow? Green shirt. So you are now going advanced, man. Next year you have already learnt. Okay. Can I make it as a 3-phase inverter? I will have to put one more leg. Becomes a 3-phase inverter. Yeah. Come again, Kanna. I'm not able to follow you. I'll go to that. Which one you want me to go to? Very good. Very nice. Good.
Hello.
Yeah.
From it, when we transition from one switch to other, we had discussed that there is some switching loss when both switches conduct. So that will lead to the shorting of the source.
Very nice. Very good question. So what is done in a practical cases, let me look at only the previous one itself. Go to the next one, yeah. Slowly. It's not there now. After this, not there, no? Okay. Yeah, we'll have to go back. Okay. Fine. We'll leave. Don't worry. We'll leave that. Okay, maybe I'll first start with this and then go to the next one. Okay. Stay here. So earlier when there is only one transistor and one diode, okay, this question is coming from the switching transient. It is not instantaneous. Firstly, let us not get into complications. And we also found that the transistor and the diode are conducting simultaneously. Is it going to lead to a short? Is it going to lead to a short? That's a question. So assuming that only the red fellows there, it is not going to become a short. Why? This total current IL will only be shared by the two fellows. Okay, one fellow will stop conducting, other one will start. So there is no problem when there is a transition from one transistor to one diode and diode back to transistor. Okay, though the switching is not instantaneous. When you put two active switches like that, there is a possibility that there can be a shoot through. Both can conduct simultaneously. So what we do is, the switches are actually switched in a complementary fashion. Okay, this is how the top switch is switched. The bottom switch is supposed to be switched like this. The bottom switch is supposed to be switched like that. But here you have a danger that there could be a shoot through. So what we do is, we delay the rising edge. We delay the rising edge. The top, we also delay the rising edge in the bottom. When you delay that by certain time, that is much longer than the turn on turn off times. 5 to 10 times then. There is no possibility. And this is what is called as dead time. This is what is called as dead time. Whenever you have two active switches, you should have dead time. Now, who will conduct during the dead time? During the dead time, the top is also off, the bottom is also off. Who will conduct? Diode will conduct. Which diode will conduct? Which diode will conduct? For red color current, this diode will current. For black current, this diode will current. Clear? Very good. So that's dead time. Okay. And you know what happens in dead time also. So I can do 3. There's one more. Instead of putting this, maybe I'll stop there. Okay. I'll just pose the question to you. Instead of putting a transistor, BJT and an anti-parallel diode, of course I can have IGBT and anti-parallel diode. I can also put a MOSFET, right? I can also put a MOSFET. MOSFET as a body diode. Okay. I can replace that by MOSFET. This is by MOSFET. So the MOSFET has some advantage. Firstly, let us say I'm having this. MOSFET can conduct in both directions. The channel can conduct in both the directions. This is going here. Okay, forget it. It doesn't want to change. Let us say it is only in one direction. The diode, we discussed yesterday that the diode drop can be high. When the diode drop is high, the loss is high. This is okay, but if the output voltage is very low, the output voltage is 5 volts. The diode is dropping 1.2 volt. Very lossy. Forget 5 volt. The output voltage can be 3.3. The output voltage can be 1.5. There are ICs that consume power at 1.5. The output voltage can even be 1.9, 0.8. In that case, if you put a diode, what will happen? Only the diode will heat up. There is no power flowing to the load. More than that, it will get heated up. So what you do is, you replace the diode using a MOSFET. You replace the diode using a MOSFET. The top is already a MOSFET. This is not for bidirectional conduction. This is not for bidirectional conduction. Here what will happen is, during the dead time, the body diode will start conducting. After the dead time, when the gate signal is enabled for the bottom, the channel will also start conducting. And when this channel starts conducting, the voltage drop will be low. So rather than have a buck converter with a freewheeling diode, if I go with the MOSFET instead of freewheeling diode, again a MOSFET for the active transistor, I may end up in reduced conduction loss in the freewheeling diode. And these are two active switches. So this buck is called a synchronous buck converter. Such a buck converter is called a synchronous buck converter. Their thing is not, the intention is not a reverse direction power flow. Okay, the intention is many a times to reduce this. Okay, but it is ready to do that too. Okay, so that's the other point that I wanted to cover. So now I think we have had a good idea of DC-DC, right? Buck, boost, and what we did, bidirectional DC-DC, and we have 2-quadrant, 4-quadrant choppers, single phase inverter, 3-phase inverter. So all these, I think, if you look at my PWM lectures, first 3-4 lectures, there is certain level of detail there. There are further questions, we can discuss that tomorrow. So tomorrow what we'll do is, we will start with the magnetics. That is something very relevant to the second year, inductors and transformers. So we'll look at magnet. The question that I've already left you is, what do you mean by magnetic field? What do you mean by magnetic circuit? When does a magnetic field become a magnetic circuit? What makes it into that? That's a question that I have already posed you. So we'll look at basic things like magnetic field and magnetic circuit. And not only through mathematics. You have seen that before we got into mathematics, we always try to get some feel. And you get a feel through visualization. So we'll try to visualize some magnetic fields. We'll try to visualize some magnetic field. And then based on that, after that, we'll go into magnetic field and reducing the magnetic field into magnetic circuit. Okay. And with that magnetic circuit, we'll go into inductors and transformers. So this is something that we will do the very first once we start. And with that, maybe after the morning tea break, we would progress into, let us say, machines. We'll take that into machine. And maybe at next 1.5 hours or so, we'll focus on machine. How do you do that now? And if there is a spillover, machine can continue post-lunch. Otherwise, we can go to control the drive. And the machine drive, sometimes depending on how the discussion goes, they also go one parallel with each other. And finally, we will also flip the motor grid side converter control. We'll see if you can do control, how can you do that? Or we'll look at how the control loops will be for a DC-DC converter, for example. So it all depends on your cause and effect. You have to understand the plant, and then it will be an inversion of that in the controller. So there is cause leading to effect 1. Effect 1 becomes cause 2 leading to effect 2. Okay. You will be, in the reverse sequence, you will be doing the controller. Okay. So for example, voltage is the cause, current will be the effect. And current will be the cause, and some say speed, torque. Current is equivalent to torque. That is the effect. Right? So that is how the plant is. So in the plant, you will have an inner current controller and you will have an outer speed controller. If you have a power supply as a voltage output, the current will be in an inner loop. The voltage of the power supply will be in an outer loop. Okay, so we'll look at some of them. And so tomorrow we'll try to look at. So we have now looked at least at the component level. One way where we looked at is electromagnetism fields. So that's, take it as one message. Don't do it as one course. Oh, hapa, fourth semester. Ha, over, man. Right? In the semester, madam, fourth. See, I said it correctly. And then, over. But that can continue. So please do that. And yeah, we'll discuss further tomorrow. Thank you.